Hey grade 12s and welcome to this video. In this video, we are going to be working on the grade 12 mathematics paper 2 for November 2023. So this paper is out of 150 marks and the time allocated to this paper is 3 hours. Okay, so we have the instructions as usual. We're going to round off to 2 decimal places where necessary and we move on to question 1. So question 1 says, truck drivers travel a certain distance and have a rest before traveling further. A driver kept record of the distance he traveled in kilometers on 8 trips and the amount of time he rested in minutes before he continued his journey. The information is given in the table below. And so, as you can see, as our variables, our x variables, we have the distance traveled in kilometers and then the amount of time that the driver rested for. Okay, so in minutes. So basically, they're really just trying to see if the distance that he travels affects the amount of time he's going to use to rest. And then, of course, with that kind of information, we can find out things like if he travels a specific distance, how long is he going to rest for? Okay, so the first question is 1.1. Determine the equation of the least squares regression line for the data. Okay, so let's go ahead and fill this information in. Also, please just note, guys, that I am using this calculator from the Play Store, so you can use your calculator. This one is different, but I will, again, also just show you the steps as well on a Casio calculator. So to fill in this information, what we're going to go ahead and do is press mode on your calculator. You're just going to press mode, and then you're going to see some options. Go ahead and choose the option that says stat. So go for stat, and when you choose stat, you're going to see that option 1 says VAR. We're not looking for one variable data. We're looking for 2 variable data with bivariate, and you're going to go for option 2 that says A plus BX. Okay, so go for option 2 and it'll give you 2 columns. So mine is a little different. I kind of just have to scroll through and go to the data side, and then I'm going to go ahead and choose A plus BX. Okay, so I already had info recorded. It always does that. So we're going to go ahead and fill this in. On the x-axis or the x column, you're going to fill in all your x values, and the y's, fill in all your y values. Okay, so now that we have all the information filled in, what we're going to go ahead and do is we need to think about what exactly the least squares regression line looks like. What does that equation look like? Well, the equation for the least squares regression line is really the equation of a straight line, and its formula is y is equal to a plus bx. So really all we need to find is the value of a and the value of b. So now that everything is recorded onto our calculator, how we will find that is like this. So to record your data, you're going to press AC, Shift, and 1 on your calculator. And once you have pressed that, you're going to go ahead and go for option 5, which says REG for regression. My option 5 is over here. So I'll just go to regression. And then once you choose that, you will see 5 options. So you can see that there's one for A and there's also one for B as well. Let's go ahead and find out what exactly A is. So you're going to go for A and then you press equal to so that it shows you the value of A. And that is negative 23.85 rounded off to 2 decimal places. So 85. And then there we got that. Then to find B, you're going to go ahead and press Shift and 1 again to get your data back. For me, I have to erase that first and then Shift 1 so I can get my data back. Then again, we're going for option 5 because we're really just trying to find variables that have to do with the regression line. So option 5 for regression. And then you're going to go ahead and go for B and say B, and that is option 2 on your side, and just say that is equal to, and then you're going to go ahead and get 0.20, and that rounds off to 2 decimal places, so that rounds up, and that is going to be 23. Okay, so that's what we have for A and B. So it means that the equation of our least squares regression line is therefore y equals A value is negative 23.85 plus our B value is 0.23, and then we have x, and that is the equation of the least squares regression line. Okay, moving on to the next question. Okay, 1.2 says if a truck driver traveled 550 kilometers, predict the amount of time in minutes that he should rest before continuing his journey. Okay, so just like what I said in the beginning, once we find the equation of the least squares regression line, and when we're using this data, we can really just use it to make predictions like how long he's going to rest if he travels a specific distance, or if he rested a specific distance, what exactly was the kilometers he traveled. Okay, we can use that to make those types of predictions. So now we're going to have to really just look at what exactly they have given us and what they're asking us for. They said that the truck driver traveled for 550 kilometers. So you're going to have to think about that. The traveling distance, right? Were those the X or Y values? Where does that belong? That is, as you can see, kilometers. Those are our X values. So it means that they have given us an X value and they clearly want us to find a Y value, because the question is they want us to predict the amount of time in minutes. The time belongs to our Y values. Okay, so because we have the equation of our least squares regression line, we can use that to make those predictions. Okay, so let's go ahead and do that. We're going to say y is equal to, so now we know that this is just an x value. We will take that number and substitute it into x. So y equals negative 23.85 plus 0.23, and then in place of x, we're going to go ahead and substitute the 550. Okay, now the great thing about these statistics is you will not lose your data, okay, if you use your calculator. You can just go ahead and press AC to just remove the number that is already written there, and then you can actually punch in this on your calculator and it should be fine. So we'll say negative 23.85 plus 0.23, and then in brackets 550. And you see what it gives us. It gives us 102.65. Okay, so there we go. And this, of course, is in minutes. You don't really have to round off. It's fine like that. So that is our answer. Okay, moving on to the next question. The next question, 1.3, is write down the correlation coefficient for the data. So the correlation coefficient is that value of R. Okay, and that R really just tells you the type of relationship that you have between your data. It tells you whether your data has a strong relationship or whether it has a weak relationship. And really all this means is if the relationship between your data is strong, for example, all this means is that you can actually rely on the data. In this situation, what we would mean by that, because we see that on the x-axis we have the distance that is traveled in kilometers, and on the y we have the time it takes for this driver to actually rest after traveling a specific distance. We're really just trying to see, does the distance he travels affect the time he takes to rest? Okay, so if it has a strong relationship, then it means that yes, we can highly depend on that. So if the correlation is strong, we can actually agree and say, yes, it means that the distance that he travels actually does affect the amount of time that it takes for him to rest. So, of course, with that being said, you will have some data where there's absolutely no correlation at all. Okay, so that's just a little explanation on what that R really means. So to go ahead and find that, what we're going to do is on our calculator, again, you can press AC just to remove that data, Shift and 1. I actually have to press AC. You don't have to. On the Casio, it's already naturally programmed to not kind of take the number you last wrote and then multiply it. Mine does that for some reason. And when you press that, you're going to have to go for option 5 again for regression. And then you see that option 3 is R. So you click on number 3 and say is equal to, and you see that R, round off to 2 decimal places, is 0.98. Okay, so that is all they asked us for there. Moving on to the next question. The next question, 1.4, says interpret your answer for question 1.3. So given an interpretation, you're really just commenting on the correlation coefficient. What type of relationship do we have between our variables, okay, our x and y variables? What we're going to do there is you can look at the correlation like this. So I try to explain it as a number line. Now, if you have, for example, a correlation of 0, then this means a correlation coefficient of 0. This means there's absolutely no relationship whatsoever between the x and y values. So in this situation, what that means is the distance that he travels and the time he takes to rest has absolutely nothing to do with each other. It's just completely random. So that is what that would mean if our correlation coefficient was 0. There's no correlation. And then if your correlation was 1, positive 1, right? What that means is that this is a perfect, right, correlation. It's perfect and it's also positive. So how we look at it is we say the strength and the whether it's positive or negative. So that would be a perfect positive correlation. In that case, that would mean without a doubt, the distance that he travels actually highly affects or perfectly affects the amount of time that it takes for him to rest. Okay. And then if it of course was -1, it would still be perfect. The only difference here is that you just have a negative value. So in this case, that will be perfect negative. This will be perfect positive. And then if it was in between like 0.5, for example, as you can see, this is positive. This would be moderate, meaning there's a 50% chance that, it actually has a correlation. So there's a 50% chance that the distance that he travels affects the amount of time that it takes for him to rest. And then if it was between here, like 0.2, for example, this is quite weak. This is a weak, of course, it's positive. So weak positive correlation, that means it doesn't even really affect it. You can't really rely on that. You can't say that, okay, the distance that he travels actually affects the amount of time that it takes to rest. And then if it was between here, like in the 0.90s, I'll call it 0.9, right? Then that is actually strong. So that's strong positive. Okay. And we also have all of these same things here for the negatives. They're just going to be, for example, a negative 0.2 would be a weak negative correlation here and so on. So when it's positive or negative, it doesn't affect the strength. That is just telling you the way the data generally goes. So your data doesn't necessarily form a straight line. However, you can draw like a straight line in between the data, which is called our line of best fit. So all that means is if we have positive, right? If our correlation is positive, it just means that your data is generally increasing. So that's what I mean by it doesn't form a perfectly straight line. However, the information is generally increasing. If it's negative, it's generally decreasing. Okay, so that was just a little explanation on how the correlation coefficient works. And so when we look at a correlation coefficient of 0.98, that would be within where? That would be within here, which is strong. So this is a strong positive correlation. And that's all you have to tell them. You don't have to start giving them explanations and saying, yes, that means that the distance that he travels actually highly affects the amount of time he's going to rest. You don't have to say that. You can just tell them what the correlation is, which is a strong positive correlation. So that's all. Positive correlation. So that's all. Okay, so that is it for 1.4, and we move on to 1.5. We move on to 1.5 and it says, at each stop, the truck driver spent money buying food and other refreshments. The amount spent in rands is given in the table below. Okay, so this is a new data. Yes, it is about the same story, but it's a new data. So we have 1, 2, 3, 4, 5, 6, 7, 8 values again, because it's still these 8 trips that they spoke about initially. So we have to calculate the mean amount of money he spent at each tuck shop. Okay, so for these types of questions, grade 12, I want you to note that you can actually use 2 methods. You can actually take these values and actually find the mean by adding up all the values that you have and then dividing it by the total number of values, the frequency, right? Or you can actually use your calculator to do this. Okay, go into the stat option. You will still get the full 2 marks for this. And you'll know this if you check 2022's November paper. They do award for full mark. So answer only still gets the full marks for this type of question if they ask you for the mean. Okay, so I'm not just going to go ahead and add it up. I'm going to go ahead and record it because I know they're going to ask us other questions about other variables in this data set. So let's go ahead and record this data. So our data may have still been on this. You can actually just get rid of it by removing it AC, and then you're just going to go ahead and press mode and go for the option that says comp. I think that is going to be option 1 on your calculator. So you just have to go for that. So I'm just going to go back, and then we're going to go ahead and press mode again, because we need to record this data. So mode, and then go for option 2, which is going to say stat. Once you go for that, this time we're not going to go for the option that says a plus bx, because as you can see, we're working with a data set that only has one variable. So go for 1 VAR. So that is option 1 on your calculator. So on my calculator, that is 1 VAR over there. I still have data recorded. I just have to get rid of it. So you're just going to go ahead and put down these 8 values that you have. And once you have everything recorded, you can go ahead and press AC, Shift and 1. And once you press that, you're going to go ahead and go for option 4 that says VAR, option 4. And when you go to that, mine is over here, you're going to find the mean. As you can see, there's the mean, okay? It is that simple. So go for number 2 and say equals, and you will see that your mean is 150. Okay, so that is our mean. Now, remember, this is money in rand, so we need to say our mean is 115 rand. So that is, it just means that he spent on average 150. Okay, the next question. Moving on to the next question. Then the next question, 1.5.2, is calculate the standard deviation for the data. So now we have to find the standard deviation. So it's good that we actually recorded the data down, because we need to use that data to find the standard deviation. You can find the standard deviation by yourself, but I would never advise you do that for 1 mark. Okay, so to find that standard deviation on your calculator, you can just press Shift and 1. I have to delete this first, then press Shift and 1. And then when our data comes up, you're going to go again for option 4, variable. And once you are there, you're going to choose the standard deviation option, which looks like that. Okay, so standard deviation of your X values. That is going to be option 3 and say equal to. And you will see that your answer is in decimals, so it is still money. So it's 50 rand, and well, that 7 will round up and turn that 9 into 10 cents. And then that's going to add to the 4 and create a 5. So that is 50 rand 50 cents. That is what the standard deviation is going to be. Okay, a quick explanation of what the standard deviation actually is. It is it's a mean value, yes, but it's a mean value or an average of, we're looking at the mean, right? And then you're looking at all the values, and some values are going to be greater than the mean, and some values will be less than the mean. And what the standard deviation really just does is it calculates the difference. Okay, so like from the mean to this value, for example, how far apart are they, right? And from the mean to this, how far apart are they? And what it does is it gets the average of those differences. So it is an average, but it's really the average of how far apart these values are from the mean. That's why we say it's a measure of, it measures the spread of the data. Now, the calculation doesn't actually go like that. That's just like a brief explanation of what that is. Okay, so that is our answer for that question. The standard deviation is 50 rand 50 cents. Moving on to the next question. So the last question for question 1 is, at how many stops did the driver spend an amount that was less than 1 standard deviation below the mean? Okay, so we have worked on questions like these in the past already. So you're going to have to think about it like this. They want you to tell them how many stops are you going to have in this data, right? That is going to be less than 1 standard deviation below the mean. So let's first focus on finding out what exactly 1 standard deviation below the mean looks like. So you're thinking about that. It means you have the mean, and you need to just go a standard deviation lower than the mean. Okay, if you're going 1 standard deviation below the mean, it means the mean has this value and you're removing a standard deviation from it. Okay, to go a standard deviation below the mean. If you're trying to go a standard deviation above the mean, then you're looking at the mean and you're just going one standard deviation above the mean. So you're adding a standard deviation there. Okay, so here mean minus standard deviation is going to get us to that one standard deviation below the mean. So that's going to be, our mean is 150 and our standard deviation is 50.50. So, well, 150 minus 50 is already 100 Rand, and then 100 Rand minus 50 cents is 99 Rand 50 cents. You can also do the calculation on your calculator. It won't affect your data. So that covers this part that speaks about one standard deviation below the mean. Then we still need to find out how many stops exactly, right, is going to be less than this value, that one standard deviation below the mean. So how many values are less than this in our data set? Well, as you can see, we can only have one value that is less than that. Everything else is above 99 Rand 50 cents. So it means our final answer is when they ask us at how many stops did the driver spend an amount that was less than one standard deviation, it was only one stop. So that is our answer there. At how many stops? Just one. Okay, so there we go. That is it for question 1. And then we move on to question 2, which has more statistics. Okay, we're on question 2, and question 2 says, at a certain school, the staff committee wanted to determine how many glasses of water the staff members drank during a school day. All teachers present on a specific day were interviewed. The information is shown in the table below. So this is the information that we have. So we have on the right the number of glasses of water drank per day, and these are in groups, okay? So people who drank between 0 to 2 glasses of water, there were 5 people, and then people who drank between 2 to 4 glasses, there were 15 people, and so on. So the first question is complete the cumulative frequency column provided in the answer book. I don't have an answer book, so I'm just going to create a column here for the cumulative frequency. Okay, so how we complete the cumulative frequency column is like this. You're just going to go ahead and take the first number, and we're really just dragging it to this side. So we have 5. And then to get the next number, you are saying this number that you have, you're going to add 15 to it. So 5 plus 15 gives us 20. And then to get the next number, you're going to say the 20 plus the 13. And that gives you 33. And then 33 plus 5 gives you 38. And lastly, we have 38 plus 2, which gives us 40. And that's how we calculate our cumulative frequency. Very simple. So there's our cumulative frequency done. Moving on to the next question. And 2.2 says, how many staff members were interviewed? So in total, how many staff members did we have in this study? There were a total of 40, because now we can see the total number of staff members because we filled the cumulative frequency. So there are 40 staff members. Okay, moving on to the next question. The next question, 2.3, says, how many staff members drank fewer than 6 glasses of water during the school day? So to find them, we can actually look at them like this. So when you look within the first class, these teachers here drank glasses of water that were between 1 to 2, okay? Not really 2 exactly, but less than 2. So these, right, there were 5 people in this category. We need to find out the teachers who drank fewer than 6 glasses. So fewer than 6. So if this is fewer than 2, then this would be fewer than 6, okay? Or less than 6 glasses. So how many teachers drank water between here? If you're looking at the class, right, the teachers who drank water within this class is 13. Yeah, that's like 4 to 6. So that is 4 to 6 glasses, right, is exactly 13. But they didn't ask you for 4 to 6 glasses. They specifically asked for the total staff members that drank fewer than 6 glasses. So as long as it's less than 6, you take it. So that means you have to take the total teachers in this class and the total teachers in this class as well, because that's fewer than 6. And even here. So really what you're going to do is, instead of adding these, you know that the number that you're going to get here belongs to everything that is in these classes. Okay, so we're going to actually say that's actually 33 teachers that drank fewer than 6 glasses, because if you added these up together, you would indeed get 33. So the cumulative frequency in this situation would have helped us to find that. So that is a total of 33 staff members. Okay, moving on to the next question. Then question 2.4 says, the staff committee observed that K teachers were absent on the day of the interviews. It was found that half of these K teachers drank from 0 to fewer than 2. Okay, that is that glasses of water per day, while the remainder of them drank from 4 to fewer than 6, which is in that glasses of water per day. So let's actually just go ahead and break that down. What they're saying is it was found that half of the K teachers, if you think about what half of the K teachers are, that's just really K over 2, or you could see that as a half K. So they're saying out of the total K teachers that were absent, half of them, right, fell into this category of 0 to 2 glasses of water. And then they said, while the remainder of them, so the remaining part of half K, the remaining part of half K would be a half K again, because if you add a half K and a half K, they give you the total K. So the remainder, so the half K, the other teachers, they drank within this class. That's really what they're saying. So we're going to have to do some reconstruction with the data that we have. We're going to have to add to certain staff members here. And what they tell us is when these K teachers are included in the data, the estimated mean is 4 glasses of water per staff member. So they tell us exactly what the estimated mean is when we finally add the missing teachers. And then now the question is how many teachers were absent on the day of the interview. So ultimately, they want you to find what? Remember how they told us that the staff committee observed that K teachers were absent. So they're actually just asking you to find the people who are absent, the teachers absent, which is K. That's what they want us to do. So find the value of K given everything they have told us. Okay, so we're going to need to reconstruct the table that we have here. So I'm just going to take this and we're going to really use this. We don't really need the cumulative frequency for this. We only need the staff members because we need to add certain things to the staff members. Okay, so remember that we had here half of the K teachers, K over 2 or half K, right? They drank within this interval. So we're going to go to the 0 to 2 glasses per day. And we know that the teachers here are not just going to be 5 anymore. We still need to add that half K teachers here. So we're going to add, you can say a half K, you can say K over 2, it's still fine. I'll actually just take that as K over 2. It's still the same as a half K, okay? Because that K is just going on the numerator to multiply into the 1. And then the other teachers, where were they? The remaining teachers, K over 2 again, they were in this interval 4 to 6. So we'll go to the 4 to 6 and we're going to put them in there. So add the K over 2 here. And the question they want us to do is find K if they told us that the estimated mean is 4. So because they told you what the estimated mean is, you have to use the calculation for the estimated mean to actually find the value of K. That's the only thing that we can do. It would have been really nice to just use maybe the total number of teachers, but unfortunately we don't know what K is. So we don't know how many teachers there are in total anymore. There used to be 40 teachers, but now these Ks have been added, so we don't know how many teachers they are. So we're going to use the estimated mean calculation, and this is how we calculate that. So I'm going to go ahead and write down these values. Let us look at these because as you can see, they do say X is greater than. So we'll call these our X values. So what we're going to do is first of all, find the midpoint of our X values. So let's find the midpoint of X. That's going to be a table on its own. And then on the other side, we're going to still take the number of teachers, the number of staff members. And this is a table that we're going to have. We'll have more things over here, one more column. Let's go ahead and put down what we have. So the idea behind finding the estimated mean, because that's what we're trying to do. We're using the estimated mean calculation to find the value of K. The idea behind finding the estimated mean, it's still the same thing as finding the mean. But you know how with the mean, they give you values, right? They can give you like 2 and 5 and 7 and 21 and 24, for example. And then you would take all these values, add them up together, find the sum of the values, and then you would divide by the frequency, right? The number of values that you have. Well, unfortunately, in group data, we don't have single values, okay? So because we don't have single values, we're just going to have to make little adjustments. What group data is really doing is, instead of taking all these numbers out separately, because then we'll have a whole lot of values, we'll have a whole lot of glasses of water per day, because that's the main point, right? The water that we have, how many teachers drank specific glasses of water. Instead of you going to these 5 teachers and asking, how many glasses of water did you drink specifically in this day? And then this teacher says, I drank 1 glass of water. And how many glasses of water did you drink? I drank 0 glasses of water. Instead of taking all of those, we have just grouped them together. So because we don't have them out like single numbers like these ones, what we do is we're going to estimate. And the estimation starts from here, where instead of taking these values separately as, oh, there's 1 glass of water and there's maybe 0 glasses of water in this class, what we're going to do is actually add these two together, these numbers together, and then divide them by 2. So that's where we're already creating the estimation. So we're really saying everybody here is going to really just drink this amount of glasses. You take the first value plus the second value and you divide it by 2. 0 plus 2 is 2. 2 over 2 is 1. So we're just saying everybody here drank 1 glass of water. It's an estimation. And that's how we find that midpoint. That's what we're going to do here. We're saying that 0 plus 2 over 2, which gave us 1. Okay, everybody in that line drank 1 glass of water. And we know that there were 5 staff members there. Then the second one again, 2 plus 4 over 2. So 2 plus 4 over 2, 2 plus 4 is 6 over 2 gives you 3. And we know that there were a total of 15. So we're saying all these 15 staff members, we're going to pretend they all drank 3 glasses of water, estimating, okay? And then we're going to go ahead and add these. 4 plus 6 is 10. 10 over 2 gives you 5. And we know how many teachers were there. That was, and I'm forgetting something. So we already added the plus k over 2. We need to include those in our calculations as well. So k over 2 needs to be there. 5 plus k over 2 is the total number of teachers that drank 1 glass of water, an estimate of 1 glass of water. And then over here, that would be 13 plus k over 2. That's the total amount of teachers that we have that drank an estimate of 5 glasses of water. So plus k over 2. And then we'll do the same for the rest. 6 plus 8 gives you 14. 14 divided by 2 is 7. So that's 7. And then you have your frequency, which is 5. And then the last one, we're saying 8 plus 10 is 18 divided by 2 is 9. And that is 2. There are 2 teachers within that category. So now we're just saying that an estimate of 9 glasses of water was drank by 2 teachers. An estimate of 7 glasses of water was drank by 5 teachers. Okay, we have roughly estimated the X values instead of asking each teacher. So here's the thing about it. Now that we have these as estimates to find the mean, you're probably going to think, oh, okay, fine. Why don't we just go ahead and, like we would have done here, add our X values and divide by the total number of teachers that we have. Yes, that's what we're going to do, but we can't do that from here. The reason why is because you cannot just say, oh, we're going to add 1 and then the 3 and then the 5, because this is 1 glass of water, yes. But how many teachers drank 1 glass of water? An estimate of 1 glass of water. That is 5 plus k over 2 teachers. Okay, so if it was just, for example, like this one, this is easier to look at. If we're looking at it like this here, we're saying that we had 15 teachers who drank 3 glasses of water. If you are actually adding that up to find the mean, it wouldn't just be, okay, just take the 3 and add it to everything else. There are 15 teachers that drank this amount of water, meaning you're going to write 3, 3, 3, 3. You're going to have to add 3 15 times. Okay, so instead of doing all of that, what we're going to do is we'll take the midpoint and multiply it by the frequency. That is to get the total amount of water, the glasses of water that was drank by the teachers in each category. So that's where we do this. We're going to take the midpoint of the x values, and we're going to multiply that by the number, the staff members. Okay, so that is the 1 multiplied by, and our staff members here is 5 plus k over 2. We're just going to have to take it like that. Well, the nice thing about this is 1 times this will just stay 5 plus k over 2. So let's keep that in mind. Then to find here the total glasses of water that was drank here, it is we know that there was 3 glasses of water, but 15 teachers drank. So that is 3 times 15, which is 45. 45 glasses of water was drank in this category in total. And then over here again, midpoint times frequency. So 5 multiplied by, we have 2 terms here, so 13 plus k over 2. And then here 5 times 7, that is 35. And lastly, 9 times 2 gives you 18. Okay, so this is what we have now. And now we have all our total glasses of water. Just like we would have done here, when calculating the mean, you take all the variables that you have, you add them together and you divide by the number of variables. That's what we're going to do here. So we now know the total glasses of water that was drank, and we're going to add all of that up together. So that is the main calculation we're going to have there. So let's go ahead and add all of that. Okay, so the sum, we're going to say how we calculate the mean is by saying the sum of our midpoint, right? The midpoint of the x values multiplied by the number of staff members, right? All of that. Add all of those together, and then we're going to divide by the number of staff members. That's how to find the mean in this case. So this is equal to, now the thing is we know the mean. So this is going to create an equation really, because we're trying to solve for k. That's the main point. That's the main goal. So therefore, the mean was what? What did they tell us that the mean was? The estimated mean they calculated was 4. So in place of mean, we're saying 4 is equal to, and let's go ahead and add up those together. So we're adding these up together. So 1 times this stays the same. So that is still 5 plus k over 2 that we have there. And I'll just leave that in red because we're trying to solve for k really. And then we're saying plus the next value we have 45 glasses of water there. And then the next one plus, we're saying 5 times 13 plus k over 2. And then plus the 35. And then plus the 18. And we're going to divide all of this by the total amount of staff members that we had. Now we can actually find that over here. You see that we can actually add these together and then find that. So I guess this one we can just do on screen. So 15 plus, let's just add the simple numbers first. So since these ones are on their own, 15 plus 5 is 20, plus 2 is 22. So we'll have 22. Then 22 plus 5 is 27, because that's that 5 there. And then plus the 13 gives you 40. So you still have 40 there, but then you have the k over 2 and the k over 2 that we still need to add together. So k over 2 plus k over 2 gives you k, okay, because it's really a half k plus a half k, which gives you a whole k. So that is what we have there, 40 plus k as our total number of staff. Now we just have to solve for x in this equation that we have built up. Let's go ahead and add the numbers that are just on their own first of all. So the 5 and the 45 gives you 50, plus the 35 would give you 85. So let's just put that down. We say 4 is equal to, and we have 85. Okay, but we still have that plus 18. So 85 plus 18. So 80 plus 10 is 90. So 95 plus 8 is 103. So we're going to have 103 there, and then so that's all our numbers added, and then we're going to go ahead and add the k's that we see. So you see that you just have first of all plus k over 2, that one in red, but then this we still have to simplify that because that still has to be FOILed. Okay, let's go ahead and just distribute here. 5 multiplied by 13, so 5 times 13 is going to be 13 times 10 is 130, so half of that is 65. So that's plus 65, and then we're going to multiply that. So we're just distributing. So 5 times k over 2. That's going to be, you see, 5 times k over 2. You just multiply numerator and denominator. So the denominator here is 1. So that just gives you 5k over 2. So that's what we have there. Okay, so we're going to have to add our k's together as well. And this goes all over 40 plus k. Okay, so now that we have this, we can go ahead and, well, we still have two things to add there. So 4 is equal to 103 plus 65 is 168. And we have our k's. So let's add our k's together. Do you see that the denominators are the same? So if the denominators are the same, just add your numerators. K plus 5k gives you 6k over 2. 6k over 2 can be simplified. 6 divided by 2 is 3. So this is actually 3k. So that's what we have there. We're going to actually just solve for k. So divided by 40 plus k. Okay, we have this equation. We're trying to solve for k, but you have a 4 on this side and you have a fraction here. So why don't you put this as a fraction, rewrite that as a fraction, and then we can cross multiply. So we're going to multiply the 4 with that and then the 1 with that. Okay, so we're going to say 4 times 40, because you need to multiply the 4 to the 40 and the k. 4 times 40, 4 times 4 is 16. So that gives you 160. And then 4 times k is positive 4k that we have is equal to, and then cross multiply like that. 1 times 168, it basically just stays all the same. 168 plus 3k. Okay, now that we have that, we can just solve for k. Put the k's on one side. You've got 4k here, and the 3k comes over and becomes a minus 3k. 168, and you have 160 here. Bring that over and it becomes negative. So therefore, k is finally equal to 168 minus 160 is 8. And that is our answer. So k is equal to 8. So what does that mean? The question was, how many teachers were absent on the day of the interviews? That was the k value, right? So it means that there were 8 teachers absent. Make sure to always answer them. The total is 8 teachers. Okay, and that is our answer. So Grade 12, you need to just really look at the things they give you and what exactly they're asking you for. Because they gave us the estimated mean, I knew that we have to use the estimated mean calculation to actually find this. So, and now you see a way that you can actually find the estimated mean. This is not always asked a lot in grade 12. In fact, I've only seen it in November papers. I've only seen this being asked twice. However, there's definitely more times. It's just from the papers that I've seen. So make sure you study everything from grade 11 and grade 12. All those concepts are very important. Okay, so that wraps it up for question 2. And that's really done for statistics. We finally move on to question 3, which is on analytical geometry. We are on question 3, and question 3 says, in the figure, we have L, S, and N, and we have their coordinates. Are the vertices of a triangle having angle SLN being 90 degrees? So that angle is 90 degrees over there. And then they tell us that LN intersects the x-axis at K. So we have an x-intercept over there. Okay, the first question is calculate the length of SL, leaving your answer in surd form. So we don't have to round off here. Let's go ahead and find this. So to find the distance or the length of a line, we use this formula, which is in your formula sheets. So we're going to say x2 minus x1 all squared plus y2 minus y1 all squared. And we're going to have SL is equal to the square root of, let's just go ahead and find these. So this is SL. So we can look at that as x2, right? And y2. So that's going to be negative 4 minus 4 all squared. So negative 4 minus 4 squared plus, and we have 1 minus 5 all squared. And then you can just substitute this onto your calculator and get your answer. So SL is finally equal to, and leave it in surd form. And in surd form, that is 4 square root 5. And that is our answer. Moving on to the next question. So the next question says, calculate the gradient of SN. So we just have to find the gradient, that's all. To find the gradient of a line, you say y2 minus y1 over x2 minus x1. So x2 minus x1. And so with Sn, see this is S and that's N, we can look at the bottom ones as the second points, okay? So x2 and y1. So we have y2 minus y1, which is negative 3 minus 5. So we're going to have negative 3 minus 5 over, and then the x's. So negative 2 minus 4. Negative 2 minus 4. And that will give us the gradient of Sn. Let's go ahead and calculate that. So if you say negative 3 minus 5, you get negative 8. And if you say negative 2 minus 4, you get negative 6. So our answer is going to be positive at the end of the day. The gradient of Sn is equal to, that becomes positive, but you see that they both have a common factor of 2. So 8 divided by 2 is 4, and 6 divided by 2 is 3. So that is our answer. Our answer is 4 over 3. Okay, so that is the gradient of Sn. Moving on to the next question. The next question says, calculate the size of theta, the angle of inclination of Sn. So because it's the angle of inclination, to find the angle of inclination, we always use this formula. We say that tan of theta, your angle of inclination, is equal to the gradient. So let's go ahead and have a look at what that line Sn looks like, and that theta really. So we can see that this is the line Sn is an increasing function. Okay, so the gradient is going to be positive. We already have the gradient. We are just trying to find that. That's all. So we don't have to think about adding any 180 degrees because the gradient is positive. We have the gradient of Sn already, so that's what we need there. So tan of theta is equal to, our gradient of Sn is 4 over 3, which we found in the previous question. So this is equal to, theta is finally equal to, we're leaving theta on its own, and we're going to take tan over. When you take tan over, it becomes the inverse of tan, which is the second function of tan, and you activate that on your calculator by saying shift tan. I'm going to say 4 over 3, and let's get the value for theta. So the answer here is shift tan of 4 over 3, which gives us 53 points, and we can round off to 2 decimal places here, 13 degrees. Okay, so that is our answer for theta. Moving on to the next question. The next question says, calculate the size of angle LNS. Let's go ahead and see how this angle was constructed so that we can actually find it. So LNS is this angle over here. Okay, let me actually just put that in a pen. So that angle over there. Okay, so looking at this, normally, well, not normally, but I was actually tempted to try and find this angle by using this. But I see that that is going to be a bad idea because we don't really have any other information. If we have this angle here, then we could have gone ahead and done that. But because we don't, I will not think about it like that. Here, we can think about it like this. So remember that to find an angle, right, you kind of just see how it was constructed. And to find out how an angle was constructed, you're going to have to relate it to an x-axis. So I'm going to redraw the x-axis. It looks like that. But I'm going to pull down the x-axis. I want the straighter one. So to pull down the x-axis to the point where this angle was created, which is right here at N. So we're going to move it down there so we can find out how exactly that angle was created. Do you see that to create this angle, if you go from this x-axis, this imaginary x-axis that we have here, you go from that x-axis all the way to this line, you're going to get this entire angle. Now, that angle would represent the angle of inclination of line LN. To find this one, if you take this entire angle and then you remove the angle of inclination, so going from the x-axis to this line over here, which is the line SN, right? Then you're going to get this little angle. If you take this bigger angle and you subtract it by that little angle, you will be left with the blue part. And that's how that angle is created. So now we know how we need to get that angle. You need to take the angle of inclination of the line LN and subtract that, okay, by the angle of inclination of the line SN, which we already have. That is 53 53.13 degrees. Let me leave it in green as well. So 53.13 degrees. So you see how that angle can appear here, but you can still draw it as another point as well, as long as you have an x-axis. So clearly all that's left to find this angle is this bigger angle over here, the angle of inclination of line LN. Now we don't have the gradient of that line, so clearly we need to find that first before we can find its angle of inclination. So let's go ahead and find the gradient of line LN. So here are our coordinates. So we're going to find the gradient of line LN, and I'm not going to use the formula because you would already have the formula on your page. So you can just go ahead and subtract. So we're saying y2 minus y1, which is -3 minus 1 over x2 minus x1, which is -2 minus -4. But when you distribute, that will become negative times negative is positive. So that's +4. Okay, so -3 minus 1 is -4. This is like saying +4 minus 2, which is +2. -4 over +2 is -2. So that is the gradient of Ln. It's a negative gradient, so you need to remember what to do there. So when we're looking at that angle, angle of inclination of Ln, do you see how big it is? It's actually an angle that goes past 90 degrees. It's not standing straight like that. It's not 90 degrees exactly. It looks like this. So it is an obtuse angle that we have over there. That's an obtuse angle. So we need to remember that rule with the 180 degrees. Let's go ahead and find the angle of inclination. So to find the angle of inclination, you say tan of the theta, but I'm going to call this theta of Ln, so I remember which angle I'm speaking about, is equal to our gradient, which is -2. And to find that, we're going to go ahead and take the tan over. So let's leave theta of Ln alone, and we're going to find the second function, use the second function of tan, and we have -2. So remember, we need to do something here to make it an obtuse angle. If you just leave it like that, if you say shift tan of -2, do you see what it gives you? -63.43 degrees. And what it's actually doing is measuring backwards, because you presented a negative value. It's measuring like that. This size is the -63.43, but we needed to give us the obtuse. And so what we're going to do here is we will add a 180 degrees to this calculation. And the idea behind that is the size of this angle is exactly 63.43 degrees. Okay, the size of the angle. Remember, angles come in sizes. Yes, when we measure them in specific directions, they may be negative because angles are supposed to be measured anti-clockwise, but this angle is measured clockwise, and that's why it's negative. But ultimately, the size of the angle is 63.43 degrees. If you want to find this angle, it's like adding the angles on this straight line, and you know it should give you 180 degrees. Okay, so you're really just saying 63.43 degrees, right, plus that angle you're looking for should give you 180 degrees. So to solve for that, you would say theta is equal to 180 degrees minus 63.43 degrees. Do you see that your 63.43 is a negative angle, just like it was here? When you say tan -2, shift tan -2, it gives you -63.43. And that's why we say plus 180, because our 180 degrees here would be positive. Okay, so that's a quick explanation why we do that. So we can go ahead and actually just add. So that's our angle there, plus 180 degrees. And so theta of Ln is equal to 116 point. Right, I'm going to round off here. The reason why is because you see that we already have one of the answers we're going to use is already rounded off. So it's fine to round off here. It's not going to affect your answer. 57 degrees. Okay, so round up to 57 degrees. And now we finally have to find the thing we're looking for. The main thing we're looking for is this angle that they asked us to find over here, right? That angle LNS. So to find that, remember again, it's the larger angle, which is the angle of inclination of Ln, minus the smaller angle, which is the angle of inclination of line Sn. And we would find it like that. So that is the angle LNS. So we say LNS is found by taking the angle of inclination of Ln, which is 116.57 degrees, minus the angle of inclination of Sn, which is 53.13 degrees. So 53 0.13 degrees, and this is equal to, and just find the answer of this. And that gives us 63.44 degrees. That is our NS. That is our angle of that angle there. Okay, so that is our final answer. Do you see that it rounds off for you? If you just used that full answer, right? Like if you didn't round off that and you just use that as this entire thing, you would just need to round off at the end. But here, it's already rounded off since we rounded off that answer. Okay, done with that question, and we finally move on to the next question. The next question, 6.3, says, determine the equation of the line which passes through L, so passes through L and is parallel to Sn. Write your answer in the form of y equals mx plus c. So it's going to have to pass through L but is parallel to Sn. So this line is parallel to Sn. So this is Sn. And if it's parallel to Sn, it's going to look like this, but it's passing through L. So this is actually what it looks like that. And we have these being parallel. So what do you know about parallel lines? Parallel lines have the same gradient because they're slanted in the exact same way. So they have the same gradient. So we already have the gradient of this line. It's whatever the gradient of Sn is. So its gradient already, we know that that is going to be 4/3. We already had the gradient of Sn, that's 4/3. And then it just passes through L. So now we can find the equation. We have the gradient and a point. So let's go ahead and work through that. So the gradient of this line is 4/3, and it passes through this point L, which was -4 and 1. You can use whichever formula you want. If you want to use the y equals mx plus c, it's fine. I usually like using the y minus y1 equals m times x minus x1, just because once you substitute and you simplify, it gives you the answer straight. But I'm going to go ahead and use this one. So y equals mx plus c, and we're going to fill in our gradient. So y is equal to, our gradient is 4/3, x plus c. And now that we have this, our equation is almost complete. All we need is a point. So you can substitute your x and your y value. So the y value is 1 is equal to 4/3, and in place of x we put our x value, which is -4, and then we have plus c. Okay, so this is c, we just have to solve for c. Let's multiply here. If we have 4/3 times -4, remember you can rewrite that as a fraction by putting it over 1. So numerator times numerator is -16, denominator times denominator is 3. So this is a -16/3 that is here, but we want to solve for c. So let's leave c on the right hand side, and we're going to go ahead and take that value over to the left hand side. Because it's negative, it becomes positive. So you still have the 1, and that becomes positive 16/3. Okay, now how you can solve for this without a calculator is 1, you just have to make sure the denominators are the same. So 1 can be written as 3/3. So that's 3 plus 16, which is 19. And your denominator stays the same. So that's 1 plus 16/3, which is c. Now that we have that, our equation is finally just y is equal to, our gradient 4/3, and we have x, and plus 19/3, like we have there. So that is our final answer there. Moving on to the next question. Question 3.6 says, calculate the area of triangle LSN. Okay, so we have to find the area of that triangle. Now, the good thing is that this triangle is already a right angle triangle. So we can easily use the area that says a half multiplied by the base multiplied by the height. Okay, and the reason we can use this is because this formula is used for triangles that have perpendicular heights. This has a perpendicular height. We can treat this SL as the height of the triangle. So that's our perpendicular height. And then this will be our base. The LN will be our base. Okay, now the thing is we already have SL. We found that in the beginning. So we need to just find LN, and then we can find the area of this triangle. So let's go ahead and find the length of LN. Okay, so these are our points that we have, and we're going to find Ln. So this is equal to, and we'll say the square root of, remember it's x2 minus x1, so we can say -2 minus -4, which of course becomes a plus 4, all squared. and then plus y2 minus y1 all squared. So that is -3 minus 1 all squared. And then substitute that onto your calculator and we'll get our answer for that. And we're going to leave this answer in third form because this is not the final answer. So let's not round off. Okay, so now we have Ln, which remember is the base of your triangle. Okay, and we also have Sn, I think that was SL, right? Which is the height of the triangle, the perpendicular height. And that is 4 square root 5. So because you have the base and the height, you can actually find this. So SL is 4 square root 5. The area of that triangle, which is triangle LSN, is a half multiplied by our base and then multiplied by, of course, our perpendicular height, which we can see over there. So this is equal to a half multiplied by, and this is 2 square root 5 times the perpendicular height is 4 square root 5 we have there. So this is finally equal to, let's just multiply these two together since they both have the square root of 5. If you say 2 times 4, you're going to get 8. And the square root of 5 times the square root of 5 is like saying the square root of 5 squared because it's really 2 of it being multiplied. And the squared would break the radical or the square root. So that just becomes a 5 because of that. And so it's 8 times 5. 8 times 5 is 40. 40 times a half, or half of 40 is 20. So the area of this triangle is 20 units squared. And that is our answer to that question. Moving on to the next question. So the next question 3.7 says calculate the coordinates of P which is equidistant from L, S, and N. Okay, let's see how that's going to work. We're going to need the diagram. Okay, so here is our diagram. For the point P, wherever it is, for it to be at an equal distance, okay, from L, S, and N, it means that when you have P, right, the distance from P to L should be exactly the same as the distance from P to S, and that should be exactly the same as the distance from P to N. That they should all be the same distance, really, from P. That's really what they're saying. Now, looking at the diagram, the only way that this can actually be possible is because how exactly would you do that? You can't say it lies in the middle. That's obviously not true, okay? This is not equal distance at all. So the only way that that would be possible is, I'll take advantage of the fact that we have a right angle here, is if we have a rectangle. So if we have another side that is parallel to LN and is exactly the same length as LN, and then we have another side that is parallel to this line here, okay, and it's also exactly the same length, and that is also 90 degrees, then you'd have a rectangle. Now, for you to have P, that P would have to lie like this. This is how we're going to have to find P. For it to be equal distance, the only points that will be at an equal distance to all these points that they mentioned is the midpoint of your diagonals. That's the only points that can actually do that. So if we had to draw a diagonal here, right, then what we're saying is that P is actually here, right in the middle. That's going to be P, and that way P is going to be exactly at an equal distance between when you look at from P to L, and then from P to S, and then from P to N. That's the only way that would be possible. So how can we actually find P now that we have constructed this? Well, we can find P like this because P is really the midpoint of these diagonals. So do you see that this line SN, right? S and N are both present. We have both those points. So we can actually use it to find the midpoint of P. So that's really what we're doing. We're going to find the midpoint of P, looking at it like that. So the way they asked the question, they didn't just tell you go find the midpoint of P. They just asked it in a way that you were supposed to look at it and then you realize that that's actually the midpoint that they're referring to. Another way that we could have looked at this is like this. For P to be at an equal distance between all these points, we could have also looked at the fact that, okay, so we're saying really we have P somewhere, and if you look at from P to L, it should be exactly the same distance as from P to N and from P to S. Another way that you could have looked at that is if this was a semicircle, okay, not the most perfect semicircle, but if this was a semicircle, and you know that the distance from the center of the circle to the circumference is your radius. So PN would be a radius, PL would be a radius, and PS would also be a radius. So that would mean that all of these are radii and P is the center. So for you to find that center, again, you could have also just looked at S and N and said that we're just going to have to find the midpoint of this line because that would be the center of this diameter. Okay, so, and we know definitely this is the case because we know that the angle in a semicircle supported by a diameter is always going to be 90 degrees. So that is another thing that we could have also looked at there. So ultimately, we just have to find the midpoint of this line. Okay, but I'd rather go with this theory because in the other theory, they didn't present any other lines. Okay, so this is what we can use. Okay, so we're finding the midpoint of line SN. So SN, we're going to go ahead and use the midpoint formula. So the midpoint of SN, the formula is x1 plus x2 over 2, and then y1 plus y2 over 2. And this, of course, is in your formula sheet. So this is going to be that point P. So P is found by saying x1 and x2. So that is 4 plus negative 2. But of course, if you say 4 plus negative 2, that multiplies and becomes negative. So it's just 4 minus 2 over 2. And then the y's, that's going to be 5 plus negative 3, which is just 5 minus 3 over 2. And then we simplify. So therefore, P is 4 minus 2 is 2, divided by 2 is 1. 5 minus 3 is 2 as well, divided by 2 is 1. So our point P is actually 1 and 1. That's the only way that that can happen. So it would have to have some sort of a semicircle there, and then P is the midpoint of your diameter. Okay, moving on to the last question in question 3.8. Then, and the last question says, calculate the size of angle LPS. So let's see where that is. So LPS. So this is the angle they want us to find. We have to calculate the size of this angle. Okay, let's see how this angle was created. How do we find this? Well, I see that we have an isosceles triangle here. But the thing is, I don't know what these angles here are here, and I can't really just assume there's certain things. So I'm trying not to make any assumptions. Okay, now let's just think, did they give us any other angle? Do we have any other angle that could help us here? I see that we have theta, but theta is just way too off. It's a bit too far. So it's not really going to help us here because theta is created by going here to there. Okay, that's that angle. So it doesn't help in LPS. But do you remember that we had this angle here? Okay, we had the angle LNS. And that angle LNS, which we found here, angle LNS, is 63.44 degrees. So this is actually very helpful, 63.44 degrees. Because do you see that we have another isosceles triangle here? Okay, so this is an isosceles triangle. It means that our sides are exactly the same. So our angles are also equal, right? So this angle over here is also 63.44 degrees as well. Now, why is that important? Do you see that this angle that they want us to find, LPS, is the exterior angle of that triangle? So to find that exterior angle, you would add this interior angle and that interior angle, and that would give us that exterior angle. So we can actually find it like that. Okay, so I'll just go ahead and start by telling them that this angle PLN is 63.44 degrees. Okay, so PLN is 63.44 degrees. Okay, and then we can go ahead and use that exterior angle of a triangle. Remember, you don't need reasons here. This is not Euclidean geometry. They didn't say with reasons. So Now we can go ahead and tell them that to find the exterior angle, which is the angle they asked for, LPS, we would say the two interior angles and add them together. So that is LPS is equal to, and it's really two sets of 63.44 degrees. So instead of just adding them individually, we could just say it's equal to 2 times 63.44 degrees and then get the answer. So LPS, so that is 2 times 63 is 126 degrees and then 0.88 because it's just double of it. So that is our angle. Our angle is, the size of that angle is 126.88 degrees if we use the exterior angle of a triangle. But we don't have to add reasons to this necessarily. Another way that we could have also used to find that angle is you could have looked at it like this. So do you see that because we have a semicircle, okay, we can actually see that the semicircle, its center was what we were looking for, the center angle, right? You know that the angle at the center is going to be twice the size of the angle at the circumference as long as it's supported by the same chord. So this angle at the center is supported by SL, and the angle at the circumference is this one over here. So that's why that would have been twice the size of this angle. Okay, you'd have to tilt your head this way to see that. So angle at the center, angle at the circumference, supported by the same chord. Okay, so that is another thing there that we could have done. Okay, so that is it for question 3. And then we move on to question 4, which is more analytical geometry. We are on question 4, and question 4 says, in the diagram, the circle with center O has the equation x squared plus y squared equals 20. So this is the circle they're referring to. And then we have G, which is 10. O is the center of the larger circle. A common tangent touches the circle at D and F respectively, such that D is the point P and -2, okay, which they didn't really write there, but there, P and -2, and they tell us that this lies in the 4th quadrant. So we just have that common tangent there. The first question is, given that D, which is P and -2, lies on the smallest circle, show that P equals 4. Okay, so we need to find the value of P. Let us look at this and just see what we have. So P is this point over here. We can look at how this point is formed. Okay, how did we get that point? Well, we were at the center and then we went P units to the right, clearly, because it's in the 4th quadrant. So we went P units to the right and then we went 2 units down, right, to get that. So if you look at that, it means that here, okay, this is a right angle triangle that we have now because I'm just forming it by just trying to find out what exactly is P, where is P, and how do we find it. So -2 would be here since we went P units to the right and 2 units down. So this is -2 and then P is this. So it means in order to find P, all we would need is this radius, OD. Now, do we have that radius? Well, in the beginning, do you see that they told us the equation of the smaller circle, the circle centered at O? So we actually have that radius. Remember that this right now, because it's at the origin, okay, it's centered at the origin. That's why it's x squared plus y squared. So centered at the origin, the equation is x squared plus y squared equals r squared. So we actually do have the radius. Okay, r squared is 20, so r is the square root of 20, which can be simplified further, of course. So we can actually use Pythagoras to solve for P. Let's go ahead and do that. So we'll leave that as P, which is really an x value, okay, because we move x units. And then this would be our y value. So y value, okay, so we'll call that y. And then this is our r, our radius. Let's go ahead and solve for P. So which is the x. So the formula will be x squared is found by saying r squared, which is the radius, the biggest one, minus y squared. And this is equal to, so x squared we know is ultimately P. So it's P squared is equal to r squared. We already have r squared. R squared is already 20. Remember, r is the square root of 20. That's to find r. But r squared itself is 20, like that. So 20, we'll put that there, minus y squared. Y is negative 2, so we just square negative 2. So negative 2 squared. Okay, so we have p squared, and we'll just have to square root both sides, of course. P squared is equal to 20, and minus, that becomes 4. 20 minus 4 is 16. P squared equals 16, and then we need to solve for p by square rooting both sides, because it's not r, it's plus minus, but based on where p is, we're going to take a certain side. So do you see that p is on the positive part of the x-axis, so we will leave that as positive. Square root of 16 is 4. So there we go. We have proven that p is indeed equal to 4. Moving on to the next question. 4.2 says E, which is 6 and 2, is the midpoint of DF. Determine the coordinates of F. So since E is the midpoint, and they already told us it's 6 and 2, so 6 and 2 need brighter colors here. 6 and 2. And we already have D, which I filled in since we know P is 4. We just have to use this to find F. Okay, so if E is the midpoint, we're really just using the midpoint formula. But the midpoint formula, and then remember you already have the midpoint. So we're really just working with it like we're finding the midpoint of DF. So looking for the midpoint of DF, remember it is still x1 plus x2 over 2 and y1 plus y2 over 2. And then that midpoint we already have. That midpoint is E. It's 6 and 2. So that is going to be our 6 and our 2. And that midpoint is equal to this calculation of the midpoint of DF. So when we're looking at DF and trying to find the midpoint of DF, because F doesn't have coordinates, we'll call it x and y. So we can say x1 plus x2 and then y1 plus y2. That is what we have there. Okay, so that will be the calculation for the midpoint. So we're going to say x plus the 4, and that is the calculation to get that midpoint. So x plus 4 over 2, and then y1 plus y2. So again, we're going to start with the y now. So y plus negative 2 over 2. So it's just y minus 2. Y minus 2 over 2. Okay, so this is the midpoint. This is the calculation for the midpoint. But what we're going to do is, because they really ultimately are the same thing, they represent the same thing, you're going to equate them. So the x value with the x value and the y value with the y value. So that means that 6 is equal to x plus 4 over 2, and 2 is equal to y minus 2 over 2. And then now we can just go ahead and solve for x. So let's just go ahead and cross multiply. This is really over 1. And so cross multiply. 6 times 2 is 12. 1 times anything stays exactly the same. So that's x plus 4 is equal to 12. X is equal to, if you take 12 and you take the 4 over, it becomes a minus 4. 12 minus 4 gives you 8. So we know what x is. It's 8. And then here we can also cross multiply again. So over 1. And multiply, that gives you 4. Multiply, that gives you y minus 2. Y equals, taking your negative 2 over makes that a positive 2. So 4 plus 2, which is 6. And so that means that the coordinates of F are, so F is just 8 and 6. And there we go. So, okay, it's just the midpoint formula, but they already gave you the midpoint. So we're just finding an endpoint. Okay, moving on to the next question. The next question, 4.3, says, determine the equation of the common tangent DF in the form of y equals mx plus c. Okay, so we already have f, remember? Because we have f, this is more than enough to actually find it. Even without f, we actually don't even need f. But we know now that f is 8 and 6. So to find the equation of this line, you just need 2 points. There we have f and we have d. So we can find this common tangent. So these are our coordinates. So to find it, we can go ahead and first of all find the gradient. So the gradient, we will say y2 minus y1 over x2 minus x1. And this is equal to y2 minus y1, that's negative 2 minus 6 over x2 minus x1 is 4 minus 8. And so that gives you negative 8. That gives you negative 4. Okay, negative and negative give you positive. And so 8 divided by 4 is 2. So we know the gradient of this line is 2. Now that we found the gradient, I'm going to use the method that I prefer using to find the equation of this straight line. So y minus y1 is equal to m bracket x minus x1. Okay, and then we just substitute. So we're saying y minus, and I'll just put it in here already. We put in the gradient, and then you substitute 1 point. I'm just going to take f because it's all positive. It's just simple to work with. So we're going to take that as our x1, and that is our y1. We substitute. So y minus 6 is equal to 2 times x minus 8. Okay, let's simplify, and we're saying 2, and we're distributing. Distribute there, we get 2x, and if you multiply it there, you get negative 16. Now, this negative 6 is still here. We can take it over, and it becomes a positive 6. Then we're still left with the y over here. So it means that y is equal to 2x, and we have negative 16 plus 6, which is really like 6 minus 16, and that is negative 10. And that is the equation of this line df or FD. Okay, so that is our equation. Moving on to the next question. Okay, 4.4 says calculate the value of t showing all working. So let's go ahead and find t. So t is this over here. T is the x value of the center of the bigger circle. So how do we actually find that? Well, remember how I always said that the previous question always helps you with the next question? Yeah, we can actually use that here. So the equation of this line that we just found is not really helpful to find that. However, the gradient is helpful. And here's the reason why. Do you see that from the center to the circumference, you have a radius in a bigger circle? What do you know about the relationship between a tangent and a radius at the point of contact? They're always perpendicular. So we can actually use that. Because this is perpendicular to this, we can find the gradient of this line. And then we have a point that this line passes through, this point. Once we substitute it, we will have the equation of that line. And then when we have the equation of that line, we can simply find this point. You see that it's t and 0, meaning we have its y value. If we substitute its y value, we'll find its x value. So we can use that. Let's go ahead and do that. So first step, we need to find the gradient of line FG. We're going to use the gradient of line FD to do that. So the gradient of line FD, that was 2 that we found here. Yes, okay, it's 2 that we have. So to find the gradient of FG would be found by saying, now what do you know about perpendicular lines? Because these lines are actually just perpendicular. If you take the gradient of the one line and you multiply it by the gradient of the other line, they should give you negative 1. So in other words, if you want to find the gradient of one line, you just take the gradient of the other line. And how do you get this m2 out of the left-hand side? Because it's multiplying, the only thing you can do is divide by it to get rid of it. So to find m1, you say negative 1 divided by the m2, the gradient of line 2. Okay, so that's what we can do there. So to find the gradient of FG, we'll say negative 1 divided by the gradient of the line it was perpendicular to, which was the gradient of FD. Okay, that gradient of 2, that line. So this is the gradient of FG is equal to negative 1 over 2, because we know that gradient already. Okay, we have the gradient of that line. Now we can find the equation of this line. So to find the equation of the line, FG, it passes through this point 8 and 6, and this is a complete point, so we can use that to find it. I'll use the quick method again, this one. Y minus y1 is equal to, and our gradient is negative 1 over 2 times x minus x1. Okay, so the point F, remember, is 8 and 6. And so this is our x1 and that's our y1. So we're substituting. Y minus 6 is equal to negative 1/2 times x minus 8. And we can simplify now. So this is equal to, if we distribute, this is negative 1 over 2x. Distribute, that's like saying, so we have negative and negative, which gives us positive. But 1/2 times 8 is saying 1/2 of 8, which is 4. And then we leave our y here, but we take the negative 6 over, and that becomes a positive 6. So y equals negative 1 over 2x plus 10. Okay, so that is the equation of the line FG. Now, to find that point T, or that coordinate T, you see that on FG, that's where this point lies. Okay, it's the x-intercept of it. But ultimately, we can just see that the y value is 0. So we can find the x value. In other words, really just substitute t and 0 in place of x and y. So that's what we're doing here. So to find g, okay, t and 0, this is our x value, this is our y value. So let's substitute. That is 0 is equal to -1/2. And then in place of x, we say t plus 10. Okay, and to solve for t, if you say -1/2 times t, you get -1/2 t plus 10 is equal to 0. But we can actually just take this over since it's negative to make it positive. So now you have +1/2 t equals 10, positive 10. And then to solve for t, we can get rid of the half by dividing both sides by a half. If you say 10 divided by a half, it's really like a doubling it. So 10 divided by a half would give you 20. And that is what the value of t is. So that is our final answer there. T is equal to 20. Okay, moving on to the next question. 4.5 says determine the equation of the largest circle in the form of ax squared plus by squared plus cx plus dy plus e. Okay, so we just need to find the equation, then distribute and leave it in that format. Okay, so with the largest circle, you see that we already found t, so we know what the full center of the circle is. It is now 20 and 0. Now that we have that, we can actually use this to find the equation of the circle. To find the equation of a circle, all you need is the center and at least one point on the circumference, which we have. We have those 2 points. So we can use that to find the circle. Okay, the equation of that circle. So G is 20 and 0, F is 8 and 6. So the equation of a circle, okay, in standard form is x minus a squared plus y minus b squared is equal to r squared. And then we're going to go ahead and substitute. So first substitute your center. Remember that the center of the circle was G, right? And that's going to be your A and B value. So we'll substitute in place of A and B, first of all, the G, right? So we're saying x minus, and this is the A, this is your B. So it's going to be like that in that order. Minus 20 squared plus, and instead of saying y minus 0, 0 is nothing. So it's y minus 0. It still stays y. And so we're going to still just have y there squared is equal to r squared. So this is the equation of that circle. Okay, so now that we have substituted the a values, we can go ahead and work on the x and y values. So this is x and this is y, and we'll substitute that into the equation. Now the point of that is so that we can find r squared, okay? Because the equation is already almost complete at this point. So now let's go ahead and substitute. So we have now, in place of x, we have 8. So that is 8 minus 20 all squared plus, and y squared is just 6. So that is 6 all squared. So 6 squared, and then that is equal to r squared. You can just substitute that onto the calculator because it'll just be easier to work with like that. And we get 180. So 180 is equal to r squared. And now that we have that, we can go ahead and substitute that r squared value into this equation because that would have been the complete equation of the circle. So therefore, this is x minus 20 squared plus y squared, which is equal to 180. So now we're not done yet because remember that they want us to put it in this format. So we need to distribute. So you have x minus 20 all squared. To distribute that, you can write it as x minus 20 times x minus 20. But remember, I always say that this method takes longer and it's better to take shorter steps so that you can avoid making mistakes. So we're going to go ahead and square the first term, and that gives you x squared. Then square the last term. If you say negative 20 squared, you get positive 400. Then to find the middle term, you say first term x multiplied by the negative 20, which gives you negative 20x. Then you multiply that by 2, which gives you negative 40x. Okay, then we have plus y squared and is equal to 180. For the sake of them saying put it in that order, okay, remember that in this order, do you see that they have nothing on that side? 0 is on that side. So let's go ahead and bring the 180 over. but also write it in the same format. You see that we have the x squared and then the y squared. So let's rewrite it like that. So therefore, x squared, and then let's write the plus y squared, and then the minus 40x, and then our constant. We have 400 and 180 is coming over. So 400 minus 180 is like saying 40 minus 18, which is 22. So this is positive 220, and this is equal to 0. So there, now it is in the format that they asked us to put it in. So there we go. That is our final answer. Moving on to the last question in question 4. Okay, the last question for question 4 says, the smaller circle must be translated by k units along the x-axis to touch the larger circle internally. Calculate the possible values of k. Okay, so that small circle must be translated along the x-axis so that it touches the larger circle internally. So here's an idea of what it means for a circle to touch another circle internally. You have this circle over here. So I'm just going to redraw it. If you have this circle, right, for it to touch the other circle internally, you really just move in it, and so that it intersects with the circle, but intersects with the circle in a way that it's still inside this bigger circle. So this is what it means for it to intersect internally. So you see here, we're going to really need this diagram. But here's the thing. That's not the only way it can intersect internally. It can do this in two ways, like this, and we could also look at it like this instead. So instead of just like that, we could also see it as moving from here and then moving along the x-axis, and then it intersects on the other parts of the circumference of the bigger circle. And there, it intersects internally like that. Okay, so we just have to figure out how to make this possible. Let's go. I'm going to just go ahead and take this diagram and let's put it down there. Okay, so the first thing we would notice about trying to do this, right, is first of all, this circle is moving along the x-axis, which is a good thing, because you notice that both of these circles, right, their center lie on the x-axis. Their center points lie on the x-axis. That's why they both have y values of 0. This one is 0 and 0. This one is 20 and 0. Okay. And another thing is we have, right, the radiuses of, or radii of these. Now here's where these are actually useful. We need to move these circles. You saw how we have a circle like this, and that needs to move along the x-axis so that it can intersect internally. So if we have that, we're just really trying to find out how can we get, how many units must we shift this circle so that it can intersect the larger circle like this. We can focus on one part of the circle, one point on the circle. We can focus on this over here. Now, the reason I'm focusing on this is because for me to make this intersect here, I have to specifically make sure that this circle, right, this part intersects at this point over here. So when I'm controlling it from here, I'm going to have to control it from this value, this point over here. So how do we find out what exactly this value is on the x-axis? What is this number here? Well, that's where the radii become important. The smallest circle, what was the equation of that? They told us initially that the equation of the smaller circle is x squared plus y squared is equal to 20, right? Remember that from the beginning? They told us that. So it means we can actually find the radius of the smaller circle. So radius of circle centered at O is, let's just call that R1. It is going to be the square root of 20, which square root of 20 can be 4 times 5, which gives you 20. Square root of 4 is 2. So 2 square root 5 is the distance, okay, that we have there. We know the radius now of that smaller circle. So to find what exactly this x value is over here, we're just going to say we're going this time from the center and we're going 2 square root 5 units to the left. So that's going to give you negative 2 square root 5. So we know exactly what that is. And what we're saying is we need to go from negative 2 square root 5 and we need to shift this circle to the right until it hits this point over here. And then we'll find out exactly by how much are we shifting it. Now, to do that, you see that we need to actually know what exactly this point is, because you need to move it from here to here. But we need to know what is this point so we know what we're moving it to. To find this point, you see that that is on the circumference of the bigger circle. We can also find it in the same way. We know the radius of the bigger circle. Well, we can find it now. Remember, we already found the equation of the bigger circle to be this at this point, and then we distributed and got it to that. So it means that your r squared is the 180. So we can find the r. So we'll call that radius 2. Square root of 180 is, okay, I'm just going to use a calculator for this. Square root of 180 gives you 6 square root 5. Okay, so we have 6 square root 5 there. Now we can find out what exactly this is. So I try not to use big calculations. Let's just focus on looking at the radiuses, radii. Okay, so to find that length, I know now that the radius of this bigger circle is 6 square root 5 units. So I'm going from 20 units in the center and I'm shifting to the left by 6 square root 5 units. That's like saying 20 minus 6 square root 5 because we're moving to the left. So it means at this point over here, the x value that we have there is just this number here, 20 minus 6 square root 5. I just didn't put it in decimals. That's the number that we have there. Guess I should just leave it in red so that we know, yeah, it's that. So that's the number that we have there. Okay, good. Now that we have these two, look at how we can find out how it was moved. How much units was it shifted so that it intersects with the bigger circle internally? You shifted it from this point and you moved it to the right to this point. How much units did we move it? Well, we can't really just see it with our eyes, but we know that you moved from here to here. So to find that distance or that difference, you take this minus that, and that would give you the amount of units you shifted that to get to that point, because we're just trying to find the distance. What is the distance between this? That's what it needs to move. It needs to move from here all the way to there. Okay, so that is the first k we can find. K is found by saying 20 minus 6 root 5 minus, and then we're subtracting it by the 2 root 5. So minus negative 2 root 5, sorry. Negative 2 root 5, which of course becomes a positive 2 square root 5 units. So here, do you see that these two are actually like terms because they both have root 5? So that's like say negative 6a plus 2a. Okay, like 2a minus 6a is negative 4a. So that is really just, we still have the 20 and then minus 4 root 5. Okay, you can see roots as if they are just variables when they are the same. So that's what k should be here. And we can, of course, just go ahead and use the calculator to get the simplified value. So what is 20 minus 4 root 5 as a decimal? As a decimal, that is k should be exactly 11.06 units rounded off to 2 decimal places, roughly about that amount for it to intersect internally. So that is the first part. Remember, it can intersect internally here, but it can also intersect internally on the other side as well. So I'm going to copy that circle, and now let's put that over here. So it can also intersect internally by it being here, and then it translates all the way to this point. There, it also intersects internally. Let me change the style and leave it to green so that we can just see it. And let's remove this just so that it doesn't distract us. Now, what we're trying to do is find out how many units do we have to move this circle so that it ends up here. Okay, so to find that, I'm going to decide now to actually use this point over here. Here's why. I wanted to intersect here. I wanted to intersect at the edge there. So I need to start using this end, the right hand end of the circle, so that when we shift it, we can find out exactly what it moves by. Okay, so we need to find this. Remember, the radius of the smaller circle is 2 root 5, right? So you're going from the center to square root 5 units to the right. And so that is exactly 2 square root 5 as an x value. The next x value would need to find, I think I should just leave this in another color rather, 2 root 5. Okay. And then the next x value we would need to find would be this one over here, to find out what exactly that is. So what is this going to be? Okay, I also just left that blue. To find that one shouldn't be difficult, because the thing is, you have your bigger circle, right? You know this is the center at 20 and 0. And then if you go from the center to the circumference, you have the length of the radius. We know the length of the radius of the bigger circle. It's 6 root 5. So it means you're going from 20 all the way to 6 root 5. That's 20, and you move into the right, so plus 6 root 5. And then that's what that coordinates would be there. That x value is 20 plus 6 square root 5 units. That's what that is there. So how do we shift this? How do we move this circle so that it moves from this point all the way to that point and lands right there? To find that, we need to find exactly what the difference is here. What is the distance? What distance did we travel? If we start from here and then we move all the way to here. To find that distance, you're just going to have to say 20 plus 6 root 5 minus the 2 root 5. And that's going to give you that. So the second way to find k, so the other value of k, is k equals, and we're going to say it's equal to 20 plus 6 root 5. And then to find that, you say minus 2 root 5, 2 square root 5. Okay, that would give you that distance of k that you must travel to get there. Therefore, k is equal to, let's just get the simplified third form answer first. 6 root 5 minus 2 root 5 is positive 4 root 5. And then the final answer here. So it's 20 plus 4 root 5, which is 28.94. So k is equal to 28.94 units. Okay, so those would be the two values of k that you can get if you're trying to move that circle so that it intersects with this bigger circle internally. Okay, Grade 12, that is it for the analytical geometry section of this paper. And then we move on to trigonometry. We are now on question 5, and 5.1 says, given sine beta is equal to 1 over 3, where beta is an element of 90 degrees to 270 degrees. Without using a calculator, determine each of the following. Okay, so this one is a little different to what they have been doing really. Remember, the types of trig diagrams they usually give us, well, that they have been giving us, is things like sine of maybe 27 degrees is equal to P, right? And then we'd have to construct that. And so these are really just trig diagrams that will always be in the first quadrant, because 27 degrees is just measured like that. So this time they are actually just going back to the normal grade 11 types that we'll deal with. These ones are also in grade 12, of course, but we usually see them in grade 11. So let's go ahead and construct this diagram. So we have 4 quadrants as usual. And what they tell us is, first of all, sine beta is 1 over 3. Now notice that this is a positive 1 over 3. So what they're really trying to tell you is that sine is positive. So let us mark the quadrants in which sine is positive. When you have your cast diagram, which quadrants do we have sine being positive? That would be in the first quadrant, which is for all. Okay, all your functions are positive here. And in the second quadrant, where sine is positive. Okay, so that's what that tells us. But then they tell us where beta is an element of 90 degrees to 270 degrees. So you need to know how the angles as well go. So remember, we measure angles anti-clockwise. So it starts at 0 degrees, then 90 degrees, 180 degrees, 270 degrees, and then back at 360 degrees. So when we're marking the quadrants that are within this interval, we're going from 90 degrees to 270 degrees. So how that works is from 90 degrees, you see the quadrants we pass. We pass the second quadrant, and then we pass the third quadrant, and there's 270 degrees. It stops there. So only these that we take. So which quadrant would this diagram lie in? It would be in the second quadrant, because as you can see, it has the most ticks. We're going to go ahead and choose that quadrant. So in other words, you could actually see that as they're asking you to find the quadrant where sine is positive, but this quadrant must lie between 90 to 270. Okay, so that's what we have over there. So we'll draw our terminal arm or our radius, and we have that down, and then draw a line down perpendicular to the x-axis. And now we can start interpreting this like this. So you see that you have sine beta is equal to 1 over 3. Well, SOHCAHTOA tells us that sine says opposite over hypotenuse. So it means this is your opposite, and that is your hypotenuse. Our opposite side is 1. So here's is our beta. We'll measure it from the x-axis going to that line. Okay, remember the reductions are meant to reduce these angles, these obtuse and reflex angles, really. Okay, so that is our beta, and we are saying the opposite is 1 and the hypotenuse is 3. So clearly the only thing we need to find is the adjacent side. So we can call this side, because you see it is on the x-axis, it is an x value, so we'll call it x. We can call this our radius, and this is a y value. That's why it's here. See, it's that y value of 1. So that is a y value. So let's go ahead and use Pythagoras to find exactly what x is. So using Pythagoras, you see that we're looking for x. So we're going to say x squared is equal to, and we're going to go ahead and start with r because it's Pythagoras, the longest side squared, which is 3. So 3 squared minus 1 squared. Okay, and then we can solve. So in order to solve, well, let's just go ahead and simplify this further. That's fine. We can do that. So this will become 9, and that's still 1. 9 minus 1 is 8. Then you have to square root both sides to solve for x. When you square root both sides in an equation, you have to include the plus and minus sign, because the positive and negative value will be a solution to this equation. So therefore, x is finally equal to, and if you square root this, please also just note which side it's on, okay? Do you see that this is on the negative part of your x-axis? So that becomes negative square root of 8. But if you simplify the square root of 8, you have to think about the fact that, well, you could use a calculator, but you have to think about the fact that there's a perfect square in 8. Okay, 4 times 2 gives you 8. So the 4 gets square rooted, it becomes 2, so it's outside the root, and then you have square root 2. So the answer here is actually negative 2 square root 2. That is our x value, negative 2 root 2 simplified. Now we can go ahead and answer these questions. So 5.1.1 says find cos of beta. So remember, SOHCAHTOA, cos is the car part, okay, adjacent over hypotenuse. So cos of beta will take the adjacent side, which is the x, it's next to that angle. So negative 2 root 2 over our hypotenuse, which is a 3. And there we go. And then 5.1.2 says sine of 2 beta. We can do that one here. So 5.1.2, since it's sine 2 beta would indicate that we are using double angles here. So the only expansion for sine 2 beta would be the expansion 2 sine of beta cos beta. And then we can go ahead and substitute with sine beta and cos beta are. So we have 2 multiplied by sine beta. Now, do you see that initially they already told us what sine beta was? They said sine beta is equal to 1 over 3. So you don't have to look for it in the diagram. We already have it. 1 over 3 multiplied by cos beta. Cos beta, we just found cos beta to be negative 2 square root 2 over 3. So negative 2 root 2 over 3. And then now we just have to simplify this. Okay, so you see this 2, you can actually rewrite that as a fraction. So its denominator is 1. Let's multiply all the numerators. So 2 times 1 is 2. And then at 2 times negative 2 root 2 is negative 4 root 2. That's what we have there. So negative 4 root 2, and then over 1 times 3 is 3, times 3 is 9. And that would be our answer for that question. Negative 4 square root 2 over 9. And then lastly, 5.1.3. 5.1.3, we have, so cos of, these are looking a lot like grade 11 types of questions here. So 450 minus beta. Do you see that this angle 450 degrees Do you see that it is bigger than 360 degrees? Okay, in your Cartesian plane, the angles end at 360 degrees. So the rule is, if you have an angle greater than 360 degrees, what you must do is subtract 360 degrees from it. And so when you do that, what we will get is cos, and 450 minus 360 is 90 degrees. So that's 90 degrees minus beta. And now do you see that you have a cofunction? And the cofunction of this is going to be equal to, so we will get sine of beta, okay? Cos 90 minus beta is sine beta. And we already know what sine beta is from the beginning. They told us it was 1 over 3. So this is just equal to 1 over 3. And that is our answer over there. Okay, so we are now done with the trig diagram. Moving on to the next question. We are now on 5.2, and 5.2 says, given cos to the 4th power x plus sine squared x times cos squared x over 1 plus sine x, we have to prove that this same thing, right? That same expression is equal to 1 minus sine x. Okay, so this is just an identity. So when you're looking at this identity, which hand side can we work with? The left-hand side or the right-hand side? The left-hand side, because the right-hand side is not much you can actually do there. So we're going to go ahead and take the left-hand side, say is equal to, and rewrite the left-hand side first. So this is our left-hand side, and we say is equal to, and now what can we do to actually simplify it? Okay, so let's actually look at this side, right? And see what they simplified it to. Do you notice that there is no cos in what it was simplified to? There's only sine. So we already know the causes need to go. Okay, now looking at our numerator, we have two terms. So there's a plus sign, so that's the first term, and that's the second term that we have there. What do you notice about these two terms? Do you see that cos squared x is common in both terms? We have a cos squared x here and a cos squared x here as well. So we can take cos squared x out as a common factor, and then we'll be left with, in the first term, you say cos to the power of 4x divided by cos squared x gives you cos squared x. That's what's left there. We're done with the first term. Now looking at the second term, what do we have left? If you take this and divide it by cos squared x, you are left with only sine squared x. Remember the plus, so plus sine squared x. And you can already see that is the identity for 1. So we have over 1 plus sine x, and this is equal to, so that just becomes a 1. So it's cos squared x times 1, which stays the same, all over 1 plus sine x. Again, do you see that we don't have any cos in our final answer, but we still have a cos here? So this needs to change. Let's go ahead and change it to cos's identity. So cos squared x times 1 is still cos squared x, and this is equal to, it's equal to, we're going to change it to 1 minus sine squared x. That is the identity for cos squared x, since sine squared x plus cos squared x is equal to 1. So if you make cos squared x the subject so that you can substitute it in place of cos squared x, you have the 1 here and you take the sine squared x over. So that is why that is the identity. Okay, so we have that, and then it's all over 1 plus sine x. So we still need to get this to look like that right-hand side. What can we do here? Well, do you see now that on the denominator you have a 1 plus sine x, but the final answer is a 1 minus sine x. So it means that they factorize this numerator. Because you have a 1, which is a square number, and a sine squared x, which is also a square value, what we can do is factorize using difference of two squares. So we'll open up two brackets, and we'll say in the square root of 1 is 1. So that means we're going to have 1 and 1. That's what gave us the 1. And then sine squared x, the square root of sine squared x is sine x. So we have sine x, and then we're just going to put a plus and minus, and that is factorized. And this goes all over our denominator of 1 plus sine x. And now, do you see that on the numerator and the denominator, those two cancel because we're multiplying all through. And our final answer is 1 minus sine x. And this is therefore equal to our right-hand side. Okay, that is proven. Moving on to the next question. 5.2.2 says, for what values of x in the interval where x is an element of 0 degrees to 360 is this same expression going to be undefined? Remember, for an expression to be undefined, if the denominator is equal to 0, then it's going to be undefined. So do you see that our denominator here is the 1 plus sine x? That was the denominator throughout. So we have, if 1 plus sine x, if we make that denominator equal to 0, then this is going to make this expression undefined. So this is what we need to solve for. 1 plus sine x equal to 0. Okay, this one is quite simple because it's linear. We don't have to factorize anything. We can just take the 1 over, and now we have sine x being equal to negative 1. We don't even need to use the general solution for this because this can be solved with a graph. Also look at the interval they asked us to find this within, where x is an element of 0 to 360. So you can actually look at this as a graph. I don't really see a need for using general solutions for this. So when we're looking at this, what we can do is this. We have a sine graph. They're saying sine of x is equal to negative 1. Your sine graph looks like this. So we have our sine graph. And where is our sine graph? Where does it have a y value of negative 1? Well, it has that at its minimum turning point over there. Okay, so that is where we have negative 1. But what is the x value that belongs to this? This is quite an easy point because you can just follow the way this goes, the trend of the original sine graph. It starts at 0 degrees, right? At 0, it's 0. At 90 degrees, it is 1. And then at 180 degrees, it has a y value of 0. Then here at 270 degrees, it has a y value of negative 1. And then, of course, at 360, it will have a value of 0. Okay, they move in intervals of 90. So you could have just used the graph to actually solve for this. So that's what we can just do. I can see clearly here that x is equal to 270 degrees. Okay, so that is the answer here. X is equal to 270 degrees. It's unnecessary to use the general solution method just because this is only going from 0 to 360. And we know that we have here at this minimum turning point, the y value is negative 1. And this will not repeat again in this interval. So it's unnecessary to use the general solution method. So I will stop here. And this is our answer. Okay, x is equal to 270 degrees. That would make this expression undefined. Okay, moving on to the next question. Okay, 5.2.3 says, write down the minimum value of the function defined by this. So do you see it's the same function? Okay, same thing. They just said y equals. So you need to find the minimum value. I think I've kind of already somewhat explained this minimum value. You see, I call this a minimum turning point. That would be the minimum value of this function right now, right? This one that we have there. But let's just look at this one. Do you see that this is the same expression they gave us initially? And we were able to prove to them that this expression was equal to 1 minus sine x. So we don't have to go start simplifying this and thinking how are we going to solve this and find that minimum value. We already simplified it. So in place of this, we can actually just say this actually means that y is simply equal to what it was simplified to, 1 minus sine x. 1 minus sine x. And now we have to find the minimum value of this function. Okay. I think I'm just going to use the graph to do this, to explain this, because I don't see any other reason to just go a long method. So now we have to be careful with the way this graph looks. It says 1 minus sine x. So note, the sine x is negative, meaning your sine graph is not going to look like this anymore. It's going to go the other way around. So instead of it going up and then down, it's going to go down and then up like that. Okay, so it is reflected in the x-axis. That's what happens when you put a negative in front of a function. Okay, so that's what it looks like now. And then you still have the 1. Please note the 1 is positive. It's a positive 1. So it means you have this negative sine x graph and then a positive 1, meaning the graph shifts up by 1 unit because it's positive, right? That one is positive. So let's just actually just look at what exactly the minimum was before. Here, when we just use the negative sine x, your minimum value would have been here. That was the minimum turning point or minimum value. That would have been negative 1 still. The maximum is still at 1. But then because of this positive 1 that we still have, this graph is going to shift up by 1 unit. So it moves up by 1 unit. So it goes, the minimum value used to be negative 1, but it moves up by 1 unit and it's now sitting on 0. So now your minimum value is 0 and your maximum value would be 2. So that's what happens there. So you can actually just say the minimum value would be, and the calculation is, when it was negative sine of x, it was initially negative 1, but because it shifted up by 1 unit because of this positive 1, okay, the minimum value is now 0. And that is our answer. Our minimum value is 0. Okay, so that is it for this particular function. And then we move on to 5.3. 5.3 says, given cos A minus B is equal to cos A cos B plus sine A sine B. 5.3.1 says, you need to use the identity above to deduce that sine A minus B is equal to sine A cos B minus cos A sine B. This question has shown up before. This is really a proof, okay? But they're not really asking you to prove the entire compound angle formula, just the ending parts of it. So you need to use the fact that you know if you have cos of, and I'm going to rewrite it just so that we can get the idea behind this, cos of an angle, and I'm going to refer to this angle as a first angle. Say cos of first angle, and then you have minus a second angle, that this should be equal to cos of the first angle times cos of the second angle. Then that sign would change to a plus. Okay, so if you have a minus here, it should change to a plus. Sine of the first angle, which was A, times sine of the second angle. And you understand why I am referring to it as first and second angle here, because they're really saying use the idea behind this, how this was expanded to now create an expansion for sine of A minus B. So let's go ahead and do that. So ultimately we need to expand sine of A minus B, but not just by saying, okay, it's equal to this. No, we're going to show them how it is equal to that using this idea. Okay, so we know that this is what we need to be working with, sine A minus B. So let me actually just leave all of this in blue so that we can actually just focus on this being our main goal. Okay, so we're trying to make this what we have right now, right? This to look like this. Do you see the first thing that we need to actually do is we have a problem here. This is sine A minus B. It's not cos A minus B. It's not cos of a first angle minus a second angle. It's sine right now. So our sine, first of all, needs to change to a cos for us to use this idea on this. So let's go ahead. How can we change sine to cos? Well, we can do that using cofunctions. So let's think about what our cofunction should be. We want to change a sine of an angle to cos. Sine of any angle, right? If you want to change that to cos, it will become cos of 90 degrees minus that angle. That's what we're going to do here. So we're changing the sine of A minus B. We're treating this as our angle, sort of like our theta. And we're going to change it to cos 90 minus that angle. So this is going to be equal to, we'll say this is cos of, and we're going to have 90 degrees minus our angle, our theta. But remember that the theta what we are referring to is this angle. So 90 minus A minus B. Okay, so good. We have changed this to cos. We just kind of need to create this idea using this. Okay, so we've changed the cos, that's good. But are we done? Let's look at what this one says. It says cos of a first angle, then minus a second angle. Right now, what we have is cos, then 90 degrees minus a minus b. Okay, it is a first angle and a second angle, but the problem is your second angle has a and b in it, which is not very helpful. So what we can do there is distribute. Let's go ahead and distribute that negative into the a and the b, the negative b. So we will have cos of, and we have 90 degrees, and that becomes a minus a, and then when it multiplies, it becomes a plus b. Okay, now the idea should still be cos of a first angle, then minus a second angle. But right now we just have three angles just there like that. But what we can do to create those two angles is we can group 90 degrees and a together. Now that is one single angle, and that works perfectly because 90 degrees minus a, you know that this can become a trig expression that is going to be, well, is going to have the angle a. Okay, for example, we see that we have cos of 90 minus a. When you're expanding that, that's going to be cos 90 minus a, and then of course you're going to have your other things, but it's still cos 90 minus a. And you know that you can simplify this to sine a. So it's still going to be simplified to a single angle that just has a. Okay, so that's why we're grouping 90 and a together. Okay, so we're still always going to compare what we have with this because we need to use this idea on this. So in here, we have cos, lovely, we also have cos. Then we have a first angle, we also have a first angle. And then we have a minus. And you see the issue here is we don't have a minus, we have a plus. We need to change that to a minus. So how can we actually do that here? Well, here we can say cos, and we have our first angle, which is now 90 degrees minus a, and we will change this plus into a minus and then bracket minus b because it's still positive b. You just removed a minus from it and then you're left with a negative b. If you distribute, you get back to positive b. Okay, so that is what we change it to. And now look at this. Do we have the same idea here? We've got the cos part that is done. We've got cos as well. We've got a first angle that is done. We also have a first angle. We've got minus in the middle. We also have minus in the middle. And we've got a second angle. We also have a second angle. And now we can use this idea on this expression. We can go ahead and expand it. Okay, let's go ahead and do that. So with this, it says if you have cos of your first angle minus your second angle, it should be equal to cos of your first angle first. And that's what we're going to do. We're going to say it's equal to cos of our first angle. Our first angle here is 90 minus a. So 90 minus a. And then they say you have to have multiplied by your cos of your second angle. So we're going to have the same thing here. Cos of our second angle. Our second angle here is negative b. So cos of minus b. Then you see that they change their sign to a plus. We also have the same idea, so we can follow it. We change it to a plus. Then they have sine of your first angle. So we'll say sine of our first angle, which is 90 degrees minus a. And then sine of the second angle, which is sine of our second angle, which is negative b. And there we go. We have expanded this using this idea. Okay, so that is actually what they're asking you to do. Use this principle, use that rule on this expression. Use it to expand that expression. Okay, so this is what we have, and let's go ahead and simplify now. Cos 90 degrees minus a will give you sine a. So that becomes sine a. And then we have cos negative b. Let's simplify this on screen. You see, if you have cos of a negative angle, what you do to make the angle positive is you add 360 degrees to it. So if you add 360 degrees and you still have minus b, you see that that creates that reduction 360 minus b, which lies here in the fourth quadrant. And you know that cos is positive in this quadrant. So this is just going to get reduced to positive cos of b. That's what happens there. See, cos 360 minus b is cos b. And then we have plus sine 90 minus a. Using your cofunctions, that gets reduced to, or simplified to, cos a. And then the sine negative b. Again, your angle is negative, so what should you do? Add 360 degrees to it. What is sine 360 minus b? Well, unfortunately, it's in cos's quadrant, and sine is not positive here, so this would be reduced to negative sine b. Okay, now we can go ahead and simplify further. So this is equal to, we still have the sine a cos b, but over here, do you see that you have positive cos a being multiplied by negative sine b? So they ultimately just give you negative cos a sine b. And that is our answer. Do you see how we were able to take sine a minus b and make it equal to its expansion using the idea of cos a minus b being equal to that? Okay, so we have finally done that. We have proven to them that sine a minus b is indeed equal to sine a cos b minus cos a sine b. And there we go. Okay, so it's part of the proof of the compound angle formula, but it's really just the ending part, not really the beginning where we find a and b and stuff. Okay, moving on to the next question. Okay, 5.3.2 says, hence or otherwise determine the general solution of the equation sine 48 cos x minus cos 48 sine x equals cos 2x. Okay, so they say hence or otherwise. Do you see now that here they are using the compound angle formula? Okay, hence or otherwise, because we just proved that compound angle, right? They want you to now use this on what we have here. Okay, now with this, because we have really weird looking numbers, and this is actually, if you reduce this, it simplifies to, if you simplify this, okay, using the compound angle rule, this is in the form of sine a, first angle, cos b, a second angle, minus cos of your first angle, which is 48, and then sine your second angle. As you can see, this is the sine compound angle rule. So we're going to have a minus b. That's what it simplifies to. But this looks terrible right now, because how are you going to actually find the general solution of this? You have sine and then you have cos. So we have to actually look at this from a different angle. And it's 5 marks. So clearly that's not all they wanted us to do. And we can't just find the answer like that. Let's just think about this. Okay, so here's the thing. The main problem here is the fact that if you simplify this, you have cos and you have sine. You don't want to have that. You can either have them just being an angle and sine, or an angle and cos, or at least them both being cos or both being sine. The problem right now is this is not working out. Even if I try to expand this to something that has sine, it's not very helpful, because if I expand it to 1 minus 2 sine squared x, well, I still can't solve, okay? I know this is not supposed to be a minus b. It's supposed to be first angle 48 degrees minus second angle x. Either ways, this is not helpful. This is really not helpful at all. I can't actually do anything with this. So here's the thing. The squares are going to complicate things a lot. So we're not going to change this, because it's always going to give us a square. The problem is not the cos 2x, clearly. The problem is how we're simplifying this part. So let's look at that. How can we simplify this? Well, if you look into what they're actually saying, they say hence or otherwise, meaning, you see what we just did now, before this? You're going to have to use that idea on this. So how can we use what we just learned from the previous question to help us here? Okay, let's think about this. To do this, instead of simplifying it to this, do you remember that they told us initially, use the fact that cos a minus b is equal to this to find the expansion for sine a minus b? That would mean that when we find that expansion for sine A minus B, we know that it's finally equal to this, right? It means we can get the sine A minus B to become a cos of something. We can get it back to cos. Okay, so if we were able to get it from this point to look like this, then that's exactly what we need to do here. So it's okay that we have sine 48 minus x, but having sine and cos is not helpful. So what we need to do is take this further. Instead of leaving it as sine, we're going to go ahead and change that sine to a cos like we did here. Okay. So do you remember that if you want to change a sine function to a cos, you use cofunctions. And that's what we're going to do here. So to change something that has sine of an angle to cos, it becomes cos 90 degrees minus that angle. Okay. So we're going to change this sine to become a cos. So we change that by saying, okay, we'll change it to cos of 90 degrees minus the angle that we have. So here we call this theta, but our angle here, the sine of, right, that angle we have is 48 minus x. So we'll change that to 48 minus x. And remember, I put a bracket here because we have two terms. Okay. So let me just erase these because I don't really need that anymore. Is equal to cos 2x. See? Now we have cos and cos, which is really what we want. Okay, let's just go ahead and simplify. We've got numbers here. They can actually simplify. So this is cos. We have 90 minus 48 degrees. And when you distribute to the x, it becomes a positive x. Is equal to cos 2x. Okay, so this is what we have, and 90 minus 48, we can actually simplify that. So this becomes cos of, and we have 42 degrees plus x, and then this is equal to cos 2x, and this looks great. Now we can actually find the general solution of this expression, this equation, sorry. Okay, so this is what we have. Okay, we have cos on both sides. You can take one cos over and then you can go ahead and find your reference angle. So the idea is once you take a cos over, you're really just trying to find the reference angle. So we're saying reference angle, but now because I'm taking this cos over, this is what we are solving for. So I'm highlighting that. That's what we're going to solve for. And then we're taking the cos over. And when cos goes over, it becomes the inverse of cos, which is the second function of cos. Shift cos on your calculator. When you have the second function of cos and the actual function of cos, because they're the inverse of each other, they will cancel. And then you'll be left with a 2x. So your reference angle here is 2x. But what you're trying to solve for, what your subject is going to be, is the 42 degrees plus x. So this is now finally, we'll say therefore, remember what our subject is the 42 degrees plus x since we took this cos over. So that is now 42 degrees plus x is equal to, and then we start solving for this function. So let's just establish how we're going to solve for this. For the sake of this video, because it is an end of the year paper and people are practicing, I know that most students use the table, the Cartesian plane method, the standard method. Okay, I do use the quick method, but I will just use that method for the sake of this video because it is a November paper. Because we have 2x, right? The x represents our acute angle. So cos is actually positive here. So we're going to go ahead and use the reductions in the first quadrant and in the fourth quadrant because these are the places that cos will be positive. In this, it's just going to be theta, meaning whatever your reference angle is. And here it's 360 minus theta. So that's what we're going to use. So we're saying our subject, which is the 42 degrees plus x, is equal to, and we'll first have the theta, our reference angle, which is 2x here. So 2x, then, because this is the cos function, it repeats every 360 degrees. So we'll say plus 360 degrees k. Now I like to say k 360 degrees. Okay, so I don't forget the k. Then we say or, and then again, our subject 42 degrees plus x is equal to, and we're going to use this the fourth quadrant reduction on it. So we're saying 360 degrees minus our reference angle, and our reference angle is 2x, so minus 2x. Then we'll have plus k of 360 degrees, and don't forget to tell them that k is an element of integers. Now we can get into solving for x in each of these equations. So we have here, we can leave x here, and when you take 2x over, it becomes a negative 2x is equal to, the 42 degrees is positive. When it goes over, it becomes a negative 42 degrees, then plus k of 360 degrees, and then x minus 2x is negative x, and we have negative 42 degrees plus k 360 degrees. We need to solve for x, not negative x. So let's go ahead and divide both hand sides by -1, or multiply both hand sides by -1. And then x is equal to 42 degrees. And that becomes a minus k 360 degrees. Okay, and then here, let's go ahead and solve for x. We have, let's leave our x on this side here. And then we have a negative 2x, so we take it over and it becomes a positive 2x is equal to, we have 360 degrees still on the right hand side. On the left, we're taking the 42 degrees over and it becomes negative, then plus k of 360 degrees. This becomes 3x is equal to, then 360 minus 42. Okay, so it's 360 minus 42. 60 minus 40 is 20. 20 minus 2 is 18. So this is 318 degrees we'll have, then plus k 360 degrees. Not yet done. We need to solve for x, not 3x. So divide both hand sides by 3. And when we divide, we'll have, therefore, that x is equal to, what is 318 divided by 3? Okay, that is 106. So 106 degrees, and then 360 divided by 3 is 120. So that's plus k of 120 degrees. And there we go, where k is an element of integers. And they asked only for the general solution. So that is the general solution for this equation. Okay, now I actually think some students would have taken a different approach. So I'm just going to actually mention that here. So here, I'll still use this same idea of that quick method, but I just want to show you that you could have chosen a different subject. So instead of looking at it like this, you could have decided to rewrite it as cos 2x is equal to cos 42 degrees plus x. And then you can take this over and then you have a reference angle, meaning this is now your subject that you have, is equal to, when you take cos over, becomes the second function and it cancels with that cos. So your reference angle now becomes 42 degrees plus x. Okay, doing the same thing again. Our subject 2x now is equal to, and we will take our reference angle, which is 42 degrees plus x, then say plus k 360 degrees. Or again, our subject 2x is equal to, then like we did here again, 360 degrees minus your reference angle. So 360 minus, but this time our reference angle has two terms, so you need to say 42 plus x in brackets and then plus k 360 degrees, of course, where k is an element of integers. So we could have also done it like this. Okay, it's going to look a little different, but it still maintains the same idea. It will still find the exact same solutions. So here's what I mean by that. You see 2x, if you take the x over, it's 2x minus x, which is x. And so your answer here is 42 degrees plus k 360 degrees. Okay, and I think it was only that part really, because this part was still fine in a way. Okay, let's just distribute. 2x equals 360 degrees minus 42. We can just go ahead and just start putting these answers down. So 318 degrees, and then that distributes and becomes a minus x plus k 360. Okay, again, you take that over, it becomes a positive 3x, and we have 318 degrees, and then plus k 360 degrees. So do you see that this one would still stay exactly the same? See, same thing, no difference there. The only one that is different is now this one. Now, you shouldn't panic and think, oh no, my answer is wrong. It's not really wrong. Okay, this will still get the same solutions. Just here you have a negative k and here you have a positive k. But remember, k is an element of integer values. Okay, here's an idea. Here's an explanation of this. If you had 42 degrees minus 3k of 360 degrees, right? And you have 42 degrees plus k 360 degrees. Okay, because that's what we have on both sides. K 360 degrees. I'll show you that it actually gives you the same answers. Let's give an example. Let's say k here was equal to 2. And let's also give where k is equal to negative 2. Okay, for these two solutions. Do you see that if you substitute k, the values of k, you're still going to end up getting the same answer. They'll just be switched around. That's all. So 42 degrees minus, and in place of k, let's start with the 2. So you have minus and 2 and the 360 degrees, right? You can get that answer. Do you see that that answer gives you negative 678 degrees, right? Now, if you substituted, instead of the 2, you substituted negative 2. What you would get here, you get a different answer, but this is just for this solution, okay? So 42 degrees minus, and in place of k, we put negative 2 instead, and then times 360 degrees, okay? So in place of that, we're going to put negative 2. Do you see that here we get 762 degrees? Okay, so here is what I mean by this. If you substitute k being equal to 2 and k being equal to negative 2 here, you will still get these two values as your solutions. So here's what I mean by that. When we go ahead and substitute 42 degrees plus 2 and then 360 using that solution that we get 762 degrees, which we know we already had. And if you change that 2 to a negative 2, you get negative 678 degrees. You see that is the exact same solutions that you're going to get, okay? Because k is an element of integers. So if you wanted to deal with it like that, okay, where you make this 2x the subject instead, it would have still been fine, even if your answer looked a little different. So even if you wanted to use this, your answer would have looked different, but then it's still the same thing really because of that k being an element of integer values. Okay, so that is it. I just decided to put a little more explanation into that just in case. And then we move on to the last question in question 5. Okay, 5.4, we have to simplify this trig expression to a single trig ratio. Okay. So let's see what we have. We have, now immediately, it's weird though, because you see sine 3x and sine x. Please, that does not become sine 4x. They're not like terms, okay? Because these are angles we're referring to. So 3x and x are just angles, okay? If you have something like 3 sine x and 2 sine x, then those are like terms, you see, because they're in terms of the same angle, sine and the same angle. Okay, so in this case, what we can do, because they're not like terms, you can't just add them together. We can actually just expand them. So let me rewrite what we have first. So when rewriting this, I'm also noticing now, you see with the 3x is quite simple to expand that. Normally, if you see something like 3x, you can expand it to 2x plus x. And these are good angles to expand it to, because you know that if you have sine 2x, you can expand that further. Sine 2x is a double angle. You can expand that further. But then now what do we do with the sine x? Now we can choose to just rewrite it there, but let's take advantage of the fact that they gave us sine and sine. Okay, they're the same function. So look at how we can manipulate this. So we have plus, and instead of writing it as just sine x, x can be formed by saying 2x minus x. So there we are using 2x and x because these are angles we can actually expand further using double angles. So let's call it 2x minus x. So please see this now as a key thing. If you ever see a situation where you have the same function and then you have sine of like 3x and x, you can actually do that. Okay, so let's go ahead and expand this. We're going to say this goes over and we have this here. Now I notice that we have a plus. Okay. We can get rid of that plus 1 because of what cos 2x can expand to. Cos 2x can expand to 3 things. But the one that we can choose is this one that says 2 cos squared x minus 1. Because when you add that plus 1, they'll become a 0. Now I'm looking at that, I'm like, I'm not really sure why I'm doing that yet. And it's not good to do things and not know why. So I'll hold on to this and then I'll see if that's necessary to actually deal with like that. Okay, let's go ahead and expand. So the reason why it is good to expand these two like this is because you see that it's the exact same function, but here you have 2x plus x and here you have 2x minus x. So eventually when you expand it, you're going to have a term that's just going to cancel because one is going to be the positive of it, the other is going to be the negative of it. Okay, so here is what we have. When we expand this using the compound angle formula, it's going to be sine, let me just start on a new line. So this is going to give you sine 2x, and then you're going to have cos x. Because it's a plus, it stays plus because this is sine. And then it says cos 2x and then sine x, right? That's what we have there. Now look at what happens when we expand this one. We have plus sine 2x cos x again, but instead of a plus, now we now have a minus, so that changes to minus, okay, minus cos 2x sine x. And do you see what will actually cancel through here? Okay, because this is negative, it's really the same thing that it expands to, just now this is now negative and this one is positive. So they will both cancel, okay, and become 0. Then on the denominator, yeah, I'm actually seeing a reason why I should change this now. Because you see now that you have sine 2x cos x, right? And sine 2x cos x, which are like terms, they're going to go together. So it's actually very helpful to get this to a point where it just says 2 cos squared x, because a cos x can actually cancel there. So we can change that. That is fine. So let's change the cos 2x part to 2 cos squared x using the expansion of the double angle formula for this. And then we have minus 1, right? Then we still have that plus 1 outside. And so these two would cancel and become 0. Okay, let's rewrite what we have now. We just have the sine 2x cos x plus sine 2x cos x. It's two of the exact same thing. So it becomes 2 sine 2x cos x. And this goes all over 2 cos squared x. Okay, this has become very simple. So now we can cancel here. Those two would cancel. So cos x and one of the cos x cancels here. And then the 2 and the 2 would cancel. And we're left with sine 2x, which can be expanded. Should be expanded really, because it will help to cancel with what we have there. Sine 2x gets expanded to 2 sine x cos x. And then this goes all over cos x. Okay, so cos x. And you see that cos x and cos x will cancel on the top and the bottom. And our final answer is 2 sine of x. And that is the final answer. And that is the last question for question 5. And we finally move on to question 6. We are on question 6, and question 6 says, in the diagram, the graphs of f of x is equal to 2 sine 2x and g of x is equal to negative cos x plus 45 degrees are drawn for the interval where x is an element of 0 degrees going to 180. Please notice that they're using square brackets here, which means that you see these coordinates 0 degrees, this x value 0 and 180 degrees, they are actually included here, meaning we have a physical point on the graph that has an x value of 0 and another point on the graph that also has a x value of 180 degrees for both graphs. Okay. And then they tell us that A, which is 105 degrees and negative 1, lies on F. So that is that point over there. Okay. The first question is, write down the period of f. Okay, so remember, the period of a graph is really just how long the graph takes to complete a cycle. So if you look at the graph of f, that is our sine graph. So this is how we'll find the period of a sine graph. You have to think about a normal sine graph. How long does it take the normal sine graph that has not been manipulated in any way to complete one cycle? So this is one cycle, right? The normal sine graph completes a cycle in 360 degrees. So how you will find the new period of a graph that has been manipulated is like this. You would take the old period, okay, so the new period is equal to the old period, which we know is 360 degrees for the sine graph, and you will divide it by the value that they are using to manipulate that period. Now, here's where we find that value. Remember, the period has to do with the angles it takes to complete a cycle. So here in f of x, what number is manipulating the angles here? That would be this 2 over here. Do you see it in front of the x? The x is your angle. So that number is what's manipulating our period. So we're going to say divided by that 2 over there. So 360 divided by 2 gives us 180 degrees. And so what it means about this graph is that this graph is not completing a cycle in 360 degrees anymore. It's now completing a cycle within 180 degrees. So that would have been 360, but now your graph is going to complete in 180 degrees, making the graph look more narrow. So it's thinner now. Okay, so that is the first question. Moving on to the next question. We're now on 6.2, and 6.2 says, determine the range of g in the interval where x is an element of 0 to 180 degrees. So within that same interval, the same domain that they gave us. So we're looking at the range of g. Okay, so the graph of g, look at how it looks. It goes like that and then up like that. Now, the truth about this is we don't really need too much of this information. However, we will look at it. Please note that the range of a function is all the possible y values of this function. So when you're looking at this function, you see that it's a function that was translated. Okay, this cos graph was shifted, and as you can see, you have plus 45 degrees. So it really means that the function was shifted 45 degrees to the left. Okay, remember, if it's plus, it's left. If it's minus, it's right. And that is when it has to do with the x, okay, when it's a horizontal shift. So when we are looking at this function, we're looking at all the possible y values that it has, okay, the first or the lowest y value right now within this domain, 0 to 180 degrees, would be this over here. Do you see that the graph doesn't go anything lower than that? So we would have to find out what exactly this y value is. Now, this is not so difficult to find out. You don't have to overthink it, because the thing is, you can see that this is on the y-axis. So its x value is 0. So to find the y value, why don't you take that x value and substitute it into this equation? So that's what we're going to do to find the y value here. And what we get is, this is negative root 2 over 2. So that is our y value. That's the lowest y value right now within this interval. And then you see that you have other y values. You have y value here and here and here, and it keeps on going. And do you see that it has a y value that has the highest point? Okay, now that y value will not be difficult to find, because remember, this is still a cos graph. And this cos graph, yes, it has a negative in front of it, okay, meaning the normal cos graph that is supposed to look like this, because it has a negative, it's now the other way around. Instead of going down, then up, it now goes up, then down, okay. But it would still mean that the highest it should reach is at 1. That is the y value of 1. That is the highest that that cos graph should go. As you can see, it goes up and then it hits the highest and then it begins to curve. So it indeed does have a maximum value of 1. And then, of course, it starts to go down. So all of these other y values, we already have them here. So what we will say for the range is that the range starts, okay, the smallest y value we have is negative root 2 over 2, and it goes all the way to 1. And those are the only y values that we will have for this graph. Here is how we can write that. So remember, there are two formats that we can use to write this. So we can write it in interval notation or set builder notation. Okay, so with the set builder notation, that's actually inequality way of writing, inequality notation. We can write it like this. We can tell them that our y values are values that are, first of all, greater than or equal to. So you see that they start here. That's the lowest you can get. Greater than or equal to negative square root 2 over 2, negative root 2 over 2. But less than or equal to the highest one was 1. That was the highest that it can go. So less than or equal to 1. And that will be in the inequality notation, okay? Or set builder notation. Or you could write it like this in that format, which is your interval notation. So we can say y is an element of, and we start at negative root 2 over 2, and then the highest it reaches is 1. Now, the brackets that you use here is very important. Do you see that in the domain, right? We have 0 as an actual x value on this graph, meaning this y value is also on the graph. That's why here we said greater than or equal to negative root 2 over 2. So here you have to use square brackets for them because these y values are actually included y values on our graph. Had your inequality look something like this, instead of just saying greater than negative root 2 over 2, then you would use a round bracket for that because it's not including negative root 2 over 2. Okay, so that is how that looks. Moving on to the next question. The next question, 6.3, says determine the values of x in the interval where x is an element of. Okay, so same interval for which f of x multiplied by g of x is greater than 0. So this is something they always bring in. Remember, if we're saying something is greater than 0, another word for this is that this is positive. So we need to find the values of x for which when we take the y values of f and multiply to the y values of g, they give us a value that is positive. The only way this is possible is if your graph of f has a positive y value and at the same time or for the same x values, your graph of g has positive y values as well. Then if you multiply them, they will also give you a positive y value. See, positive times positive is positive. The other way that this can actually happen is if your y values for your graph of f is negative and your y values for your graph of g are also negative, and then they would also give you a positive result. So this is what we're looking for. We're looking for places where the graph of f and g are both positive or where they are both negative. So let's go ahead and look for that in our diagram. Okay, so where is the graph of f and the graph of g, both positive and both negative? We're going to go ahead and use this vertical line. You can use a ruler. So you're going to go through it like this. So let's start here. You see, they said greater than 0. They didn't say equal to 0. So you can't include points like this. You see, this graph, the graph of f, here at this point of 0, it has a y value of 0. This one has a y value of that negative square root 2 over 2 that we found. If you multiply them, that's 0 times that negative root 2 over 2, that gives you 0. So we can't include the actual x value of 0 degrees. That's not going to work out here. But if we keep moving, do you see here now that look at this part of the graph over here? The part of this graph of f has a positive y value. And for the same x value, that's why we use a vertical line, the part of this graph of g, this point here has a negative. See, if you take that positive y value and multiply it by negative, you get a negative result. We're looking for positive results. So they need to either be both positive or both negative. Let's keep moving. As we keep moving, you see that's still positive and negative. We don't want that. Positive and negative. Then something happens here at 45 degrees. At 45 degrees, the graph of g hits the x-axis. So it has a value of 0 and a positive. So we won't take that physical point of 45 degrees. But when we go after 45 degrees, do you see now that this has a y value of a positive y value? I don't know what that is yet, but that's a positive y value. And then this also has a positive y value there. They're both positive. If you keep moving, also both positive. Again, they both have positive y values. Keep moving, even at the point of intersection, they both have positive y values. And as we keep moving, they have positive y values here until 90 degrees. Because at 90 degrees, the graph of f hits the x-axis and it now has a y value of 0. We can't take this because this is 0 times a positive will give you 0. We're not looking for where it gives us 0. So you see that it worked all through there. Let's just highlight that. So with that, we're saying that it worked here. It started after 45 degrees and it started working here like that. So really, let's just mark it like this. At 45 degrees, after 45 degrees, we started seeing that these graphs both had positive y values, and they stopped at 90 degrees. They didn't have any more positive y values after 90 degrees. So they worked all through here, okay, for both graphs. There, they both have positive y values there. We will take those coordinates. And then let's go ahead and keep moving. Now you see that here the graph of G has a positive y value. The graph of F has a negative y value. We can't take any of those. Okay, that's positive and negative. Can't take. And unfortunately, it doesn't happen anywhere else again because they just keep being positive and negative all through. And then here they are 0 and positive. Okay, so that's the only place that it works. And so we can go ahead and write down these coordinates, or really the values of x for which this happens. You see, it happens between 45 degrees all the way to 90 degrees. This can be written as x is greater than, but not equal to, okay, 45 degrees, but less than 90 degrees. And that would be our answer for that. Okay, again, this is the inequality notation. We can also write it in interval notation, which would be x is an element of, and then we'll say it's going from 45 degrees all the way to 90 degrees. But remember the kind of brackets you're going to use here, because 45 and 90 are not included x values. You will use round brackets. Okay, there we go. So that is our answer for that question. Moving on to the next question. The next question, 6.3.2, says we need to determine the values of x for which f of x plus 1 is less than or equal to 0. Okay, guys, they always do this. Remember, they just put in this plus 1 here. You don't have to put the plus 1 and start thinking about it like, if I shift the graph up, where is it less than or equal to 0? No, you can just take the 1 over. So this function is actually reading as f of x, this inequality, is less than or equal to negative 1. Okay, and now we can go ahead and find the places where the graph of f has a value that is less than or equal to negative 1. Do you remember they gave us a specific point that had that negative 1? Okay, the point they gave us was this, A. So when you're looking at the graph of f and you're looking for parts of the graph that are either less than or equal to negative 1, it means that at negative 1, we are only going to take parts of this graph that lie below negative 1 or that are equal to negative 1. So that is over here. See, all of these have y values that are less than negative 1. Okay, and we're also going to take the places that are specifically equal to negative 1. So at this point over here, your y value is negative 1. At this point, it's also negative 1. And we need to just tell them the values of x for which this is actually happening. Okay, so for the first part, it's simple because they already gave you the coordinates of A. They said it's 105 and negative 1. So it means that this x value over here is 105 degrees. But then we would need to find this one over here. Now, how you find this here is you're going to have to think about how the graph, right, works, the original function of the graph. So I'm going to give a brief explanation. I hope it's not going to take too long. I'm going to give a brief explanation as to how you can actually find the angles in your function when you know what the y value is. Let's take a look at what the graph of f of x looks like. You see, it says 2 sine 2x. So this graph has already been manipulated, okay? The period has been changed. The amplitude has been changed, okay? That all of these things have been altered already. But we're going to try to understand what the normal graph looks like and then understand how that relates to this and how we can actually get this value over here. So here is the thing about the sine graph. The normal sine graph, the original one, the mother graph, is y equals sine of x. And that graph is quite simple to draw. In fact, if you just have a calculator or you're using one of those special angle formulas, okay, like the OHA rule or even the triangles or the circle, you can actually figure out what these are. So the sine graph looks like that, right? And you just have to remember the key points on it. You know that at this point over here at 0, it has 0 degrees and 0. And then here, this is where it hits the y value of 1. And then here it has 180 degrees, 270 degrees, and the y value here is -1. And then 360 degrees. That's what the sine graph looks like. And if you look at our sine graphs, we're in luck because at least they didn't change the sign of that value there. Okay, it's still also going up and then down. See, like here. But we just have to understand exactly what this y value of -1 would be on the original sine graph. So let's think about it like this. Do you see that this graph in front of sine, there is a 2? So instead of it having a maximum of 1 and a minimum of -1, it now has a maximum of 2 and a minimum of -2. So what would that mean for this -1? What is the y value of -1 on the original sine graph? Because this was changed to 2, it just means that all these key points here, this 0, the 1, the -1, they were just doubled. So a y value of -1 on the original sine graph would actually be half of this. It's not -1 here, it's actually -1/2. So if you found what the y value of -1/2 is, you'd be able to actually find out what these ones are. But also remember that the amplitude has also been altered, and we'll speak about that as well. So let's first of all focus on finding out what exactly the x values would be for this graph if our y value was -1/2, okay? And that's really the equivalent of -1 in this altered sine graph. So let's look at that. Now you see that it has actually two places where it's equal to -1/2. It's here and here. And here's how we can actually find this. So we're trying to find out where is y, at which value of x or which values of x is y equal to -1/2. Here's how we can do that. So we're trying to find out where sine of x equal to -1/2, and we can actually use the method of solving for general solutions to do this. But remember, we're only trying to focus on from 0 degrees to 360 degrees right now here. So this is what we can do. We're going to find our reference angle. To find the reference angle, you take sine over, but I'm going to use the Cartesian plane method. So I'm not going to say shift sign of this negative. We will take the positive angle, but we're going to keep in mind that sine was negative, okay? We're not going to say -1/2, we're saying shift sine of 1/2, okay? So we just want to find the reference angle. That is 30 degrees. So because sine is negative, now to find exactly what angles these would belong to, you're going to have to think about on the Cartesian plane, where is sine negative? Sine is negative in the third and the fourth quadrant. So that is tan and cos's quadrant. Now what are the reductions that you have here? You have 180 degrees plus theta, and you have 360 degrees minus theta. So to find exactly what these values are, we're going to use these reductions, and you will see that we will find those values. So here, first, when we're trying to solve for x is equal to 180 degrees plus theta, which is 30 degrees. And of course, you'll say plus k of 360, but we don't have to do that. We're not looking for general solutions. We're just looking for this in here. Okay, so x is equal to 210 degrees. Or the second value here, so we know what this one is 210 degrees. The one here, the one further, that is going to be where x is equal to 360 degrees minus 30 degrees, which gives you 330 degrees. You see how we're able to find that? Now we have to take into consideration that this graph that we have was altered. They changed the period of the graph. So you see how the period used to be 360 degrees and now is 180 degrees. It just means it was cut in half. So that's how all the angles on your graph will also behave. They will also be cut in half. They'll also be halved as well. So how we're going to look at this is like this. You see the 210 degrees, because remember, the equivalence of negative a half here is -1 because of that 2 that they put in front of this. So we had 210 degrees here, right? We know that at negative a half, the x value is 210 degrees. But you know that the function that we have has that 2 in front of the x. So what you're going to do is take this angle, this solution that you have here, and you're going to divide it by 2. You see that if you take 210 degrees and you divide it by 2, you get 105 degrees. That is the 105 degrees that appears here. And so to find that second one over here, because they have tampered with the period of the graph, okay, the period is now completing in 180 degrees. You're going to take that 330 degrees and also divide that by 2. Okay, all the angles here are going to be divided by 2. And we can actually see that because do you see that this graph completes a cycle, right? In 180 degrees. Here it completes in 360 degrees. Here's another thing. Do you see that at 90 degrees, your sine graph is touching the x-axis? Here at 180 degrees, it's touching the x-axis. All the angles here just get divided by 2, represented here. Okay, so 330 degrees divided by 2, we got what? 165 degrees. So we know exactly what angle is here. It's actually 165 degrees. So this took longer because I'm actually explaining it. Normally, you would learn these graphs and then you do these calculations really quickly and then you'll be able to write it down. Okay, so that was a little detailed explanation on it. I always apologize for making it too long, but I also just want to make sure that you guys actually do understand what's going on. And thank you to all the students who actually said it was fine to be explaining it in more detail because I really don't want to just rush through this paper. Okay, perfect. We now know what these two angles are. And now we can actually answer the question. So remember, we're just trying to find out the values of x for which this exists, okay? For which f of x is less than or equal to -1. So that starts at 105 degrees. And then you see it's values that are greater than 105 degrees, all these values, but less than or equal to 165 degrees. And so that would be our answer. We can write it as x is greater than or equal to 105 degrees, but less than or equal to 165 degrees. And there we go. And then you can also write it in interval notation, which is going to be x is an element of, and we're going from 105 degrees to 165 degrees. But then remember, we have is equal to, meaning 105 and 165 are included values. So you need to use square brackets. And there we go. So that is our final answer there. Moving on to the next question. Question 6.4 says, another graph P is defined as P of x is equal to negative f of x, okay? And then we have D, which is k and -1, and that lies on P. Determine the values of k in the interval, again, in that interval above. So we have to actually find the values of k if we have a new graph called P, and P is found by saying negative f of x. Okay, so just put a negative in front of f of x to find the equation of P. And we have to find exactly what this coordinates, this x coordinate k is if the y value is -1. Okay, let's go ahead and do that. I feel like I should have left that diagram that I drew, but it's fine. We'll just work with it without it. So let's go ahead and rewrite this equation. Since it is negative f of x, it just means you're going to take the graph of f and put a negative in front of it. So the graph of f was that 2x, right? That sine 2x, 2 sine 2x. And so we put a negative in front of it, and now we have negative 2 sine 2x. So the k points they want us to find is this D, which is the D point they want us to find is k and -1. And with this point, do you see that the y value is -1, the x value is k? So solve for k if y is equal to -1 on this graph of P. So because y is -1, we're replacing, in place of p of x, that y value, we're going to replace that with -1 to find out exactly what this is. And so we have -2 sine of 2x. And we need to really solve for x because that's going to give us our k value. Now, you can do this using general solution, but it's going to take really long. So I'm going to actually deal with this thinking about what the original function looks like and what the translated one, the one that has been reflected, okay, across the x-axis. That's why it has a negative in front of f of x. So when we have this like this, do you see that they're just both negative? So you can just multiply them both by -1 to make them positive so that we can properly relate this with the graph we have, because the graph of f of x is 2 sine 2x. It doesn't have a negative, right? So that's what we can do. Or if you like, you can see this as taking this -2 sine 2x over, so it's now a positive 2 sine 2x, and then taking the -1 over and becomes a +1. So ultimately what they're asking you is, tell us the value of x for which 2 sine 2x is going to be equal to 1. You already have the graph 2 sine 2x. It's this function over here, the graph of f, that is 2 sine 2x, right? And we need to find out, where does it have a y value of 1? So do you see that it has a y value of 1 at 2 places, here and here? Again, if you know what the original function looks like, you know exactly what these two values should be. So you can think about the original function. I'm just going to redraw everything like I did before. So because this is the original sine graph, when we are looking for where 2 sine 2x is equal to 1, okay, what that means for your original sine graph is, because this, everything is doubled on the y-axis, okay? So the 1 here is actually referring to a half. Here's another way to actually see that. You see, you have 2 sine 2x is equal to 1. If you were just trying to get the sine 2x so that you can find out what exactly that is, you would try to get rid of the 2. And it's multiplying, so you have to divide both sides by 2. So we have sine 2x is equal to a half. Do you see that? That's why that 1 that we see here on the original sine graph, it's actually a half. So in other words, what you're trying to do here is, first of all, find out, where is this sine graph going to have a y value of a half? It's here, clearly, this value over here, and this value over here. And we can just go ahead and find out that. First of all, this is actually quite simple to find out because we're working with the positive y value. So sine is positive here. So we can just say, where is sine of x equal to a half? And go ahead and find that reference angle. So take sine over. If you say shift sine of a half, you get 30 degrees. So that's what we have here. Because sine is positive in the first and the second quadrant. Okay, so you would only use the reductions x is equal to 30 degrees, of course, plus k of 3 is 60 degrees, but we don't have to include that. We're not looking for general solutions. Or you say x is equal to 180 degrees minus your reference angle. That would be sine's reduction there, which gives us 150 degrees. Okay, so now do you see that here on the original sine graph, where the graph of sine x is equal to a half, is at 30 degrees and at 150 degrees. So what would that be on this graph that has the period been changed? Okay, the period is changed here. So remember, all the angles, to find them from the original function, you would just divide these angles by 2, because what happened is we put 2 in front of the x. The same way the period of the graph changed from 360 to 180 degrees, you just halve all these from the original function to find the one from the function that has been manipulated. So that over here is going to be, we'll find that by saying 30 degrees divided by 2, which is 15 degrees. So this is 15 degrees here. And then we'll find this one by saying that 150 degrees divided by 2. 150 divided by 2 is 75 degrees. So there we go. You can work through these by thinking about how it relates to the original function. Okay, so those would be the x values at which your y value has that. So our values for k for this equation where -1 is equal to -2 sine of x, you see we simplified it. The values for k is this, where k is equal to 15 degrees or k is equal to 75 degrees. Okay, so I put it like that because why would you want to work with a -2 sine of 2x graph? We don't even have that function there. You would have to draw it and then start thinking about where those values would lie. What we could have just done is, okay, we see that we have negative and negative. Just get rid of the negative so we can relate it to our function 2 sine 2x, which we actually have drawn in our diagram. Okay, so that is the answer for that question. K is equal to 15 degrees or k is equal to 75 degrees. You can also show those workings. Okay, done with that. Moving on to the next question. Then the last question for question 6 is 6.5, which says the graph of h is obtained when g is translated 45 degrees to the left. Determine the equation of h. Write your answer in its simplest form. Okay, so in its simplest form. They told us that the graph of h, this is a new graph they're introducing, is obtained when g is translated 45 degrees to the left. When you have left or right movements, these affect the x. Okay, now it's moving 45 degrees to the left. Remember, if the graph moves to the left, you add. If it moves to the right, you subtract, okay, from the x. So there we're going to have x plus 45 degrees. That's what's going to happen there. So in the notation format, we're saying that h of x, this new graph, we get that by taking the graph of g, right? And what we're doing to the x, because it's moving to the left, is we are going to add 45 degrees to the x. And that's really what we're doing. And we need to now just solve and find out what exactly the equation of h is going to be. Okay, so what is the equation of g? What is that graph? That was negative cos x plus 45 degrees that we already had. So let's go ahead and put that down. Okay, so this is h of x is equal to, and now in our graph of g, wherever you see x, you're going to add 45 degrees to it. Okay, so our graph of g is negative cos, and then you see x, then you can add the 45 degrees now if you want. So 45 degrees, but remember that it already had plus 45 degrees. So it already had plus 45 degrees. And so when you simplify this, h of x is equal to negative cos of x, 45 and 45 give you 90 degrees. And you see that we have a cofunction. Now this cofunction, cos x, so only this part, right? Cos x plus 90 degrees, that gives you negative sine of x. So it's one of those ones that actually becomes negative. It's the only one with the 4 cofunctions that actually becomes negative. So it means that this is now h of x is equal to, we still have that negative outside, but this becomes negative sine x, right? And because of that, when we distribute at the end, our final answer is positive sine x. And there we go. That is the answer for the last question in question 6. And then we move on to question 7, which is on 2 and 3D trigonometry. We are on question 7, and question 7 says, in the diagram, S, T, and K lie in the same horizontal plane. Okay, so in the same horizontal plane, and RS is a vertical tower. The angle of depression from R to K is beta, and they tell us that TSK is equal to alpha, and TS is equal to P meters, and the area of triangle STK is Q meters squared. Okay, so the first question is to determine the length of SK in terms of P, Q, and alpha. So really just find SK. Okay, so SK is over here. How does this relate to P, Q, and alpha? Well, it probably just goes back to what they said, because we're looking at P. Here's P. Q. Q is the area of this triangle. And then alpha is that center angle. So we can use the area that was given, the area of this triangle, because you see this triangle, includes the dimensions that we're looking for. Okay, they mentioned that, and they mentioned this, and they mentioned alpha. So we can go ahead and use the area rule because you saw the sides that they're taking, the side, and then the angle in the middle. So this is the area rule we're going to use. So the area of this triangle STK, triangle STK, is equal to, so how we would find the area of this triangle normally is like this. We would say a half multiplied by, since this is our center angle, we'll take the side next to the center angle, which is ST, but we already have a length for that, that's P. So multiply by P, then multiply by this side, which we're trying to look for, which is SK. And then you say sine of the center angle, which is alpha. Okay. And the thing is, we already know what the area of this triangle is. The area is Q, since it's Q. And then the meters cubed is just the unit of measurement it's in. So this is equal to, and we have, so when we're simplifying this, remember, we're just trying to solve for SK. So we just have to make that the subject. So when we're multiplying, you can see that we just have a half P SK. I'm just going to leave SK as the, in front. So it's SK, then we have multiplied by a half P sine of alpha, because I'm trying to just leave this on its own because they are multiplied all through anyways. Now that SK is on its own, do you see that to leave this alone on the right hand side, you need to get rid of all of these. So we're going to divide both hand sides by a half P sine of alpha. And then we have, so now this is gone and we have SK now as our subject. So leave SK here. SK is equal to, and this is what is left. So be careful with the half. Okay, half is a fraction already and it's on the denominator of a fraction. So you can look at it like this. The coefficient of Q is actually an invisible one. So if you said 1 divided by a half, even if you use a calculator, it would give you 2. So what you have here is 2Q over, and then on the denominator we have P sine alpha. And that is our answer. 2Q over P sine alpha is our expression for SK. Moving on to the next question. Then we move on to 7.2, which says, show that RS is equal to 2Q tan beta over P sine alpha. So we have to find RS this time. So let's go ahead and see where RS is. RS is over here. Now remember, the previous question or the previous solution will help you with the next question. In the previous question, we found this. We found SK. So let's just keep in mind, we already know what this is. So RS is part of a right angle triangle. To find this, we can use, you don't have to use Pythagoras necessarily, but you can use the trig functions because the trig functions have to do with a right angle triangle. So katoa, right? That's what we're going to use here. Let's see how we can work through this. You see, with your trig functions, you need a reference angle, an acute angle. We have the 90 degrees, but we don't really have any acute angle. But it just depends on how you look at it. Do you remember that they told you that the angle of depression from R to K was beta, the angle of depression? So what this means is, when you're thinking about an angle of depression, you have a flat plane, okay? You just have to kind of look at it like this. You see this line, if we extend it, even if it's not extended, it's actually parallel to this line. We really look at that angle of depression as if like if this is an eyeball, you're kind of like looking down, right? That angle that it creates is your angle of depression. So these two lines are actually parallel. So because they are parallel, do you see that we have alternate angles here? Now, those are alternate angles, meaning this is beta. So there, now we have an angle inside this triangle and we can actually use that to find RS. So the thing is, we have our reference angle beta. We are looking for RS, right? And as you can see, RS is your opposite side. But the only thing we have in this right angle triangle is SK, which we found in the previous question. Okay, we found what SK is. So what we're working with is the opposite side to beta and the side here, sk, which is the adjacent side. So which function are we going to use to solve for beta? We would use tan because that is the OA, TOA. So we're going to use tan. So we're going to find tan beta. Let's just say tan beta is equal to, and it's going to be equal to the opposite over the adjacent, OA, TOA. Okay, so opposite over adjacent, which is RS, we're looking for that over SK. RS over SK, and now we can go ahead and simplify. So we already found SK, so let's substitute it in place. I can go ahead and call this, so tan beta is equal to, we can do the whole thing on dividing, but yeah, I guess it is necessary here in a way. So we'll say RS, and then we are dividing by this, okay, SK, which we found to be 2Q over P sine alpha. So we'll divide it by that. Okay, now at this point, we don't really need to tip and times. Here's why. You see, we just want to solve for RS, that's all. So if we're trying to solve for RS, we just need to think about it like this. So we can think about it like this. What do we need to get rid of so that we can get RS on its own? We need to get rid of this. So think about what this is doing to RS. We are dividing by this. So in order to get rid of it, you would multiply, okay, by it. So even if I left it like this as RS over this, to get rid of that, you're really just going to take your equation and multiply both hand sides by that expression, 2Q over P sine alpha. But what you do on this side, you must do on that side. So as well, we'll also multiply here by 2Q over P sine alpha. Okay, so this would be gone now, because we really just did the opposite to get rid of it. And now we'll have RS on its own. So we can just leave it as RS is equal to, then rewrite what we have here. You see that you have a numerator and denominator will multiply it. So the 2Q and the tan beta can multiply since they're both on the numerator to become 2Q tan beta. And then your denominator is the P sine alpha multiplied by the invisible denominator of 1, which is P sine alpha. And that will be our answer for that question, like they have already said. So there's our answer. Okay, moving on to 7.3. 7.3 says calculate the size of alpha. Okay, so they're not going to give us alpha. If alpha is less than 90 degrees, okay, so that's probably just a hint to help us to know, okay, yeah, this is alpha. Or it might be because maybe we have the ambiguous case here, but we don't really deal with that particular topic in the CAPS curriculum, I've noticed. But okay, calculate the size of alpha if alpha is less than 90 degrees. And RS, interesting, they're giving you things here. So RS is equal to 70 meters, P is equal to 80 meters, Q is equal to 2,500 meters squared, and beta is equal to 42 degrees. Yeah, so you can already see which equation we're going to use. We're going to go ahead and use RS's equation because it includes everything except for alpha. Okay, let's go ahead and take that equation. So let's substitute. They told us that RS was equal to 70, which is equal to, we have 2 Q, they said was 2,500, so 2,500, and then tan beta is 42 degrees, and then this goes all over P, which is 80 meters, so 80 multiplied by sine alpha, and what we're trying to just solve for is alpha, so we kind of have to just get that to be the subject. Okay, we can actually do this really quickly. Instead of trying to manipulate things and stuff like that, you know how when you have an equation for like x plus 2 is equal to 5, right? And you want to get to a way to solve for x. I know that we normally say we take it over, but what really happens is you subtract 2 from both sides of the equation, right? And when we work with multiplication and division, we've kind of been working with that idea. When we have things like x times 2, or let's say 2x is equal to 10, for example. So when we have equations like this, right, we normally say, okay, we'll just divide by 2 on both sides, right? which is the same thing as saying, okay, here we'll subtract by 2 on both sides. But we could have also just said, since 2 is in front of x, it's multiplying by x. So to get rid of it, if we were taking the 2 over, the 2 that was multiplying by the x now starts to divide by the 10. So if it was a multiply by 2 on one side, when it goes over, it becomes a divide by 2. Okay, so it's still the same principle that we've been using. We've just been doing it in a different way. So that's what we can do here. We want sine of alpha to come over here. So do you notice that sine of alpha is being divided by everything here? When you take it over, it now moves from where it used to be. It was on the denominator before. When you take it over, it will move to the numerator. Okay, and it's now getting multiplied by that. But I actually don't want to leave that there. What I'm going to do is take the 70 this side as well. So do you see that the 70 was on the numerator initially? So the 70 is on the numerator. When we want to take it over, it's going to go to the denominator. So we already have the 80, and now we're going to have a multiply by 70 next to it. It just changes its position. If we don't do it this way, we can end up just like cross multiplying, which takes really long. That's why I'm just doing it this way. And so sine alpha is equal to, we already moved the 70 over to the denominator. And then on the numerator, we still have everything else that was there. So 2 times 2,500 is actually just 5,000. And then we have tan of 42 degrees. And do you see now we have numbers all through here? Don't mind the tan. The tan is still a number because it's tan of 42 degrees, okay? So we can actually solve for alpha. Let's just go ahead and simplify this on the calculator. Let's just simplify faster. Okay, so it gives us decimals. I don't really want decimals. So I'm actually just going to find out what exactly the 5,000 over that 80 times 70 is. So we have sine alpha is equal to, that gives us 25 over 28. But we're going to now leave our tan 42 on the numerator. So really you just have 25 over 28, tan 42 degrees. That's what we have. And now to solve for alpha, specifically just alpha, you can take your sine over. In other words, what you're doing is you're finding the inverse. You're using the inverse of sine on both hand sides of the equation. Okay, arcsine. So we're taking that over, and its alpha is equal to shift sine or arcsine of every number that we have here. So this is 25 over 28 tan of 42 degrees. And then we'll just find exactly what that is. So round off to 2 decimal places. Alpha is equal to 53 point, that rounds up to 51 degrees. And that is our answer in the last question for question 7. Okay, that concludes it for the trigonometry part of this paper. And then we move on to question 8, which is on Euclidean geometry. We are on question 8, and question 8 says, in the diagram, O is the center of the circle. Use the diagram to prove the theorem which states that the angle subtended by a chord at the center of the circle is equal to twice the angle subtended by the same chord at the circumference. That is, prove that TOP is twice the size of TKP. Okay, so another proof that I already have on my channel, but I'm still going to deal with it here since this is an official November paper. Okay, so this is what we're going to do. We're just going to create a construction. We really only need one thing, a line, okay? And that line is a line that is going to go through K and O. Okay, it's going from K to O and then just extend further, okay? And the reason is because we're trying to create an exterior angle looking at these 2 triangles that we have. So let's go ahead and name this K1, and that is K2, and then this is O1, and that is O2. And then make sure you write down any constructions. Also, let me just name this point that is extended to. Let's just call that Q. So extend KO to Q. Okay, so there we go. And in your exam, you will have a page to actually create these constructions on. Okay, so now that we have this is the idea we are going to use. So you see that we have 2 triangles. So this triangle, OKT, and this triangle OKP. So you see, in this triangle, what we're going to do is, let's look at the fact that we have an exterior angle. So an exterior angle of a triangle always comes from one side of the triangle, and then it's just an extension of that side. So we do have that over here. This is the exterior angle O1, angle O1. So let's go ahead and tell them that angle O1, the exterior angle, is going to be equal to, remember, the exterior angle of a triangle is equal to the sum of the two opposite interior angles. So if you add these two angles, you will get the exterior angle of the triangle. So it's equal to angle K1 plus angle T. That is what we have over there. And then we can write the reason. Exterior angle of a triangle. And then something we should notice about this green triangle again is, look at the fact that OK and OT are radii, okay? So they're equal in length. So because you have two of the same lines here, you have an isosceles triangle. And that would mean that angle K1 is actually equal to angle T. So that's what we're going to mention now. Tell them, but we can see that OK is equal to OT, okay? Because they are equal radii. So you can just say radii. And then therefore, because they are equal, those two angles are equal. So angle K1 is actually equal to angle T. So we can actually update this equation that we had. See, this means that angle O1 is actually equal to angle K1. And because these two are already equal, K1 and angle T are equal, we can actually just replace angle T with angle K1. So plus angle K1. And if you simplify this, this is O1 is equal to two things that are exactly the same are being added. So it's 2 angle K1. So that's what we have there. And now we're done with the green triangle. Let's move on to the triangle OKP. So in this triangle, do you see that we also have an exterior angle? We have this angle over here, which is the exterior angle. Let me just remove these. This angle should be equal to the sum of the two opposite interior angles, which are angle K2 and angle P. So angle O2 equals angle K2 and angle P. K2 plus angle P. Again, this is because of the exterior angle of a triangle. Grade 12, I forgot something. So here, this is supposed to have a reason. So because these two angles were equal, I can't just say, okay, they're just equal, then they actually have a reason for that. It's because it's not because it's an isosceles triangle. Sure, it is an isosceles triangle, but the reason that we use here is because we have angles opposite equal sides. Okay, so that's the reason that we have. The angles lie opposite equal sides. And then these are just conclusions, so it's fine. Okay, then we have angle O2 being equal to angle K2 plus angle P, and that is again because we have an exterior angle of a triangle being equal to the sum of the two opposite interior angles in this red triangle, that plus that. But do you also notice that in this triangle, OP is a radius and OK is also a radius, so they're equal in length. So we can tell them that, but we know that OP and OK are equal. Let me just say OK is equal to OP because they are equal radii. Then, because we have two radii being equal, it means that these two angles are therefore equal. So, angle K2 is equal to angle P because of angles opposite equal sides. Okay, we have an isosceles triangle there. So, angle K2 is equal to angle P because of angles opposite equal sides are equal. So because these two are equal, we're doing the exact same thing again. We're going to update this equation. It means that angle O2 is actually equal to angle K2, and in place of P, angle P, we replace that with angle K2 since they are now equal. And so this means that angle O2 is actually equal to 2 angle K2. Now, here is where everything comes together. Do you see that what they asked us to prove is that angle TOP is equal to angle 2 times the size of angle TKP. Angle TOP is made up by adding angle O1 and angle O2 together. If you add those two together, you get that TOP. So we're going to add them together. Tell them that angle O1 plus angle O2, and let's find out what it's equal to when we add them. Angle O1, like we have proven, is 2 angle K1. 2 angle K1 plus angle O2, which is 2 angle K2. And when we add these two together, we can actually just say it makes up this angle TOP, angle TOP. So let's actually sum that up. Therefore, we're saying that this is actually equal to TOP. And now when simplifying this, do you see that we have a common factor of 2? We can take out 2 as a common factor, and we're left with angle K1 plus angle K2. But angle K1 and angle K2, when you add them up in the diagram, do you see what they make up? They make up the angle TKP that they refer to. So because they make up that, we're going to therefore tell them that angle TOP is equal to 2 times the size of that angle TKP. And there we have proven this theorem, just like they told us to. Okay, so that is for 5 marks. Moving on to the next question. We are now on 8.2, and 8.2 says, in the diagram, O is the center of the circle, and ABCD is a cyclic quadrilateral. OB and OD are drawn. So we have the center, okay, and these are radii that we have. They say if O1 is 4x plus 100 degrees, and angle C is x plus 34 degrees. Calculate, given reasons, the size of x. Okay, so let's just fill in what they told us. First of all, they told us that angle O1 is 4x plus 10 degrees. And angle C is x plus 34 degrees. If we know that, then how can we actually solve for x? Well, first of all, let me just put this out there. Please, this is not a cyclic quad, okay? It is a quad, sure, but it's not a cyclic quad. A cyclic quad has to have all its points on the circumference of the circle, really, like that. So in order to actually solve for this, we can actually use this cyclic quad. That will be very helpful. And we can focus on using the opposite angles of the cyclic quad, because we're looking for a way to create some sort of equation, right? If we wanted to use this quad over here, because it's not a cyclic quad, we would need to have angle D2 and angle B2 and then add up all the angles in the quadrilateral, and angles in the quadrilateral should add up to 360 degrees. But as you can see, we don't know what B2 and D2 are, so we can actually use this. So we would have to find angle A and say that the opposite angles of a cyclic quadrilateral add up to 180 degrees. So the first thing is we need to find out what exactly angle A is. So angle A is at the circumference, and it's supported by this arc DB or BD, right? Do you see that the center angle O1, is also supported by that arc BD? So it means that the angle at the center is twice the angle at the circumference because they're supported by the same arc. So what we're going to do there is tell them the angle at the center, which is angle O1, is supposed to be, well, is twice the size of the angle at the circumference, which is angle A, because they're supported by the same arc. And then we can give them the reason. And then let's fill in what we have. So this is to solve for angle A. That's what we're trying to do. So let's substitute what we actually do have. We have angle O1. It is 4x plus 100 degrees is equal to 2 times the size of, we don't have angle A because that's what we're looking for. So 2 times the size of angle A. And you see now that we can actually use this to solve for angle A. So you have to remove the 2 by dividing both hand sides by 2. And then we have now finally that angle A is equal to this whole thing divided by 2. So 4x divided by 2 is 2x. 100 divided by 2 is 50 degrees. And that's what we have. Angle A is 2x plus 50 degrees. Now that we have this as 2x plus 50 degrees, we can now use the fact that the opposite angles in a cyclic quadrilateral add up to 180 degrees. So that is angle A plus angle C should give us 180 degrees, and we'll put our reason down. And then angle A is 2x plus 50 degrees. Angle C is x plus 34 degrees like we have there, plus x plus 34 degrees, and this is equal to 180 degrees. So you just have to solve for x now. So 2x and x give you 3x added, and then that is plus 84 degrees is equal to 180 degrees. Then 3x, we're going to leave that on the left. We have 180 degrees minus 84 degrees. So 180 minus 80 is already 100. 100 minus 4 is 96. So that gives us 96 degrees. And then we're going to divide both sides by 3 to get x on its own. And it means that x is therefore equal to 32 degrees. Okay, because 9 divided by 3 is 3. 6 divided by 3 is 2. So there we go. 32 degrees is our value for x, and we have also included the reasons. Okay, so that is it for 8.2, and then we move on to 8.3. Okay, so we're on 8.3, and it says, in the diagram, O is the center of the largest circle, of this circle, and OB is the diameter of the smallest circle. So you see that will pass the center. It's a diameter of the small circle. And chord AB of the largest circle intersects the smaller circle at M and B. The first question is, write down the size of angle OMB, provide a reason. Now, I know when we're looking at this angle, OMB, it looks like, okay, it's a line from the center of the circle, okay, to the midpoint, and then people will just say, oh, it's 90. But it's not really because of the bigger circle. Remember that I told you that OB is a diameter of the smaller circle. Now, the angle supported by a diameter will always be 90 degrees. So that's why that is 90 degrees, because of the smaller circle. So it's equal to 90 degrees because of angle. It's an angle in a semicircle. Okay, so angle in a semicircle. And then 8.3.2 says, if AB is equal to 300, okay, not 300, but the square root of 300 units, and OM is 5 units, so this is 5 units, we need to now calculate, given reasons, the length of OB. Okay, looks simple enough, because we have a right angle triangle. We have the line from the center of the circle being perpendicular to the chord. So that would mean that this line would bisect this chord, because the line from the center of the circle perpendicular to the chord always bisects the chord. So these two are equal. And so if this is the square root of 300, we can find the length of MB. It would be half of this entire length. Okay, so we can actually do that. We're really just going to tell them the length of MB. So we know now that AM should be equal to MB. And the reason they're equal is because of that line from the center of the circle, okay, perpendicular to the chord. Okay, so we have the reason. So this would mean we're just trying to find the length of MB since it's part of this right angle triangle. So MB would be equal to half the length of AB, because they are equal in length. So half the length of AB, you can just say the length of AB and divide it by 2. So this is the length of MB, square root 300 over 2. Okay, now that we have this as root 300 over 2, we can finally use Pythagoras to find OB, which is what they want us to find OB. So this is, we're going to use Pythagoras, and you see that OB is the largest side, okay? So that is the hypotenuse. So saying OB squared is going to be found by saying MB squared plus OM squared. But we already have these lengths, so I'm just going to put them down. So the MB is square root 300 over 2. So that's squared plus OM squared, which is 5. So 5 squared. So OB squared is equal to, and we can find out what that's going to be. That's really just going to be 300 over 4, because the root's going to break, and then plus 25. Okay. And 300 over 4 plus 25, OB squared is equal to 100. Then when we square root both sides, you don't have to include the plus and minus because this is Pythagoras. Okay, we're working with lengths. So OB is equal to the square root of 100, which is 10 units. Okay, so we don't include that plus and minus only because we're speaking about length specifically. So that is the length of OB, 10 units. Okay, and that concludes it for question 8. And then we move on to question 9, which is on more Euclidean geometry. We're now on question 9, and question 9 says, in the diagram, we have ABCD is a parallelogram, okay? And they've already shown you that the opposite sides are parallel. With AB being equal to 14 units, let's just go ahead and fill in as we see. So they told us that AB is 14 units, so that is 14. AD is produced to E such that AD is to DE is equal to 4 is to 3. So AD is to DE. So you see, these are ratios. They are not the actual lengths of these sides. They're really just telling you how it's been shared. So this entire side of AE has a specific length, and how it is shared within AD and DE is that AD has 4 parts. So we'll just call that 4A so that we know it's not the length, it's just the amount of parts it gets from the entire length. And then DE is the 3. Okay, so AD is 2. So 3A, AD is to DE. Then they tell us that EB intersects DC in F. Okay, so just an intersection there. And EB is equal to 21 units. So EB, that entire thing is 21 units. So I can actually say 21 there. That is the actual length. The first question is calculate with reasons the length of FB. So we have to find FB. Okay, that is actually perfect for this diagram that we have. Here's why I say so. You see that they already gave you EB. They gave you the length of EB and they want you to find FB. So since they gave you FB, the side that we can use, because these lines are already parallel, we can go ahead and use the proportionality theorem and we will use these sides. So because they told us FB, find FB, we are going to pair that with AD on this side. That's the one that's going to be in proportion with it. And then we have the AE because we have EB, the entire length of EB here. So we can use the entire length of AE here. Okay, so we can go ahead and start like this. So I like to start with the side that I'm actually looking for because they said find FB. I'm going to say FB over, and then we'll take the length that we actually have on this side, which is the EB. So FB over EB is equal to, and the side it is paired with is this side. So we have AD over the entire length of AE. So AE. And the reason for this is the proportionality theorem, right? But the reason we give is because we have a line parallel to one side. I can just say parallel to one side, okay, of a triangle. That is our reason over there. Okay, and now we can start solving for this. So FB is what we're looking for. We have no idea what that is yet. And we have over EB. The length of EB is 21 units. So that's 21 is equal to, and we have AD, which I called 4A. And I'll leave it as 4A because it will simplify still. Over, and then we have AE. And our AE is this entire length over there. So do you see that together with the 4A and 3A, that makes 7A. So we have over 7A there. Okay. Now you can't just write the A's if you want. If you don't want, it's also fine because what actually happens is the A's would cancel. Okay. So this is what we actually have. And now to solve for FB, you see that the only thing stopping you is this 21 over here. So to remove a denominator of 21, you would multiply by 21. And we do that on both sides because this is an equation. So therefore, FB is equal to whatever 4 over 7 times 21 is. Okay, 4 over 7, because we have diagonally, do you see that these numbers can actually cancel? They have factors, common factors. So 7 goes into 21 3 times. So we have 3 there. And then 7 divided by 7 is 1. So ultimately what we have is 4 over 1 times 3, which gives us 12. So FB is equal to 12 units. And that is our answer for that question. Okay, moving on to the next question. The next question, 9.2, says, prove with reasons that triangle EDF is similar to triangle EAB. So let's go ahead and mark these triangles first. So we have EDF and EAB. We'll mark that one in green. So this is triangle EDF and then triangle EAB. Okay, so that is EAB. So this is actually quite simple to work with. It's really just working with these two triangles, and because these two lines are parallel, it's going to help us a lot to prove that these triangles are actually similar. So let's go ahead and just introduce the triangles. We'll just say in triangle, and we have EDF, and second triangle is triangle EAB. Okay, so what do we have equal first? So you don't have to use the sides here because, as you can see, we don't know what these sides are. We can focus on using the angles to prove that they are actually similar. So with the angles, do you notice the red triangle and the green triangle? They both have a common angle, angle E. So we can actually go ahead and tell them that angle E is equal to angle E, and the reason is because it is a shared angle. Okay, the second thing that is equal, the second angle that is equal in both triangles are, so those would be these. Look at that. So do you see that we have parallel lines? And the type of angles you can find on parallel lines are fun angles. Do you see that we have corresponding angles over here? So this angle is equal to this angle. So we can actually tell them that in these triangles. In this triangle over here, we'll call that angle EDF. So angle EDF should be equal to the other angle EDF is equal to. And in the second triangle, we don't really have to call this EAB because you see that angle A is just on its own. There's no line separating and, creating a confusion on whether that is actually angle A. So that is just angle A on its own. So we have is equal to angle A. And the reason is because we have corresponding angles. And the third one, if you like, you can actually just say third angle in a triangle. The third angle, you could say this angle is equal to that because of the third angle. But it's also because we also have corresponding angles like that as well. It also creates an upside down F. So we have corresponding angles there as well. Okay, so that is angle EFD is equal to angle B. And that's what we're going to tell them. Angle EFB is equal to angle B. Okay, so that is what we have there. EFD, sorry. I said EFB. Angle EFD is equal to angle B. And it's also because of the same reason, corresponding angles. Okay, so now we can conclude and tell them that triangle EDF is indeed similar to triangle EAB. And this is because we have three sets of equal angles. So we can say angle, angle, angle. And that's our answer. Okay, so we're done with that. Moving on to the last question in question 9. The next question says, calculate with reasons the length of FC. And this is for 3 marks. So FC. Okay, so this length over here. Okay, so to find FC, do you see that FC is a part of this parallelogram they mentioned? So that would mean that we actually know the entire length of DC because the opposite sides in the parallelogram are equal. Then DC is 14 and they're telling us to find FC. So to find FC, we would first have to find DF since we know the entire length of this. So if we find DF, we will know exactly what FC is. Okay, let's focus on finding DF. How can we actually find DF? So do you see that, okay, one side that we have here is AB. So because they're giving you this side of this bigger triangle, they probably want you to use similarity. You see how we proved that the two triangles were similar? That's probably what they want us to use. So look at how we can actually take these sides so that they make sense. We want to find DF. They have given us AB, so we know we're definitely going to take those sides. And how we take them is by looking at our conclusion here. So do you see that the two sides we were focusing on was DF? We want to find DF, and we can see that we already have AB. So I'm going to focus on taking DF. DF is here, so DF, right? It's the second and the third letter. So if I say DF, then I'm going to have to put that over the second and the third letter in the second triangle. It has to be like that so that it is in proportion. That is why it's very important to name your triangles properly so that when you conclude and you're using the dimensions, it actually does work out. So that is DF over AB is equal to, so we know that we can use those two sides because one we're looking for, one we have. Now, you see that in this triangle, we're going to have to take two sides, right, from these two triangles that we actually have, because this one is missing right now. We have this one. So if you have two sides that you actually have, you see that this equation will be used to find DF. We can actually use it to find DF. So let's focus on finding two sides in these triangles that are actually there. So let's look at that. In this triangle, I can already see straight away we have 21. We have the entire length of EB. So since we're using EB, the side that is going to go with that is going to be EF. We're going to have to take EF, meaning we need to know exactly what EF is. And here's the thing. Even if you didn't know you were supposed to take EF, because you know that you already have the length of EB, you could have looked here and said, okay, I know I need to take EB. And then the side that will go with that in the first triangle would be EF. Okay, so that's how we know we have to actually take it like that. So we started with DF over AB. And so we're going to say it's equal to EF over EB. Now, the thing here is we don't really know what EF is yet. But do you remember that in the first question, they asked us to solve for FB, which is 12 units. So if we know that this is 12 and the entire length is 21, then what is this? We'll find that by saying 21 minus 12. Okay, so I would actually mention that that's actually something we're supposed to do in the beginning. That was actually the first thing we were supposed to do. So find the length of EF. We'll tell them that EF is found by saying 21 minus 12, which is equal to 9. So now that we know what EF is, and you don't even need a reason for that because it's just subtraction. And now we can go ahead and work with this. So we are going to use this like that. Your reason here would be because you had similar triangles. You can specify the triangles that were similar as well. Okay, so now that we have that, we're going to say therefore. So we are still looking for DF. That's actually something we don't have. So we're saying DF over and AB. What is AB? We already have that. That is 14. So DF over 14 is equal to EF over EB. So EF now we know is 9 units over EB. The entire length of EB is 21. So 9 over 21. And then you see that to solve for DF, you're going to have to get rid of the 14 because it's on the denominator. You're going to have to multiply by 14 to get rid of it. So times 14 on both hand sides, and therefore DF is equal to whatever this is going to give you. But we can actually just calculate it. So do you see that 21 and 14 have something in common? They have 7 in common. So 14 divided by 7 is 2. 21 divided by 7 is 3. But then 9 divided by 3 is 3. So it's really just 3 multiplied by 2, which is equal to 6. So DF is therefore 6 units. And we have solved for DF. But then that's not the final question. They actually asked us initially to solve for FC. So let's find FC. Now that we know that this is 6 units, and you remember that this shape that we have is a parallelogram. So these two sides are equal. Okay, so how would we find FC if we know now that DC is equal to 14 units? We would simply just say 14 minus the 6, and then that would give us FC. Okay, so I can just tell them, first of all, that these two are equal. So DC is equal to AB, which makes it equal to 14. So we can tell them that DC is equal to AB. Okay, therefore DC is equal to 14. And this is because it's a parallelogram. Opposite sides of a parallelogram are equal. Okay, and now that we have DC, we can find FC by saying that FC is equal to the entire length of 14 minus the 6 units. So 14 minus 6, which means that FC is therefore equal to 8 units. And that is our final answer. Okay, FC is equal to 8, and that is it. So this part was actually very okay. It was not really a headache at all. That was question 9. And then we move on to the last question for this paper, question 10. Okay, we are on the last question, question 10. And question 10 says, in the diagram, PQRS is a cyclic quad. So we have this as a cyclic quad, PQRS. Okay, such that PQ is equal to PR. That's something they didn't put down, so we're going to have to put it down. We know that PQ is equal to PR. So let's mark that. So remember, these two lines are equal. Okay. The tangents to the circle through P and R meet QS. So the tangent is this, that's definitely a tangent, and that, okay, through P and R, that they meet QS, so that's this line, at A. Okay, so they're just describing the lines now. We're just going to take note of things that are tangents, and if there's like a center, things like that, because those would be very important. Okay, and then they tell us that RS is produced to meet the tangent. So these are just lines. RS is just produced to meet the tangent, okay, at B clearly. Okay, so tangent AP at B, yes. And then they tell us that PS is produced, so PS is produced to meet the tangent. So we can see it's AR at C. And PR and QS intersect at M. So that's QS and PR. They just intersect at M. Okay, so there's no center. There's no center of the circle here, so we can't really use anything that has to do with the center of the circle. We just have tangents. Okay, do you remember that if you have tangents, I'm just mentioning this now, tangents drawn from the same point to a circle. So it's really coming from A to the circle, right? That they are equal, meaning from A to R, that is equal to A to P, right? So that's something that we can also just keep in mind. Okay, the first question says, we need to prove that angle S3 is equal to S4. Okay, so in other words, just start from S3 or start from S4. So if we start from S3, you need to move it around, find out what it's equal to, and eventually get it to be equal to S4. And I like what's going on here because there's a lot of lines crossing, so we can use vertically opposite angles over there. But let's just see, how can we actually move angle S3? Remember grade 12, so I have said this, I think this was in the 2022 paper. You don't look at these things and then just start guessing. You have to look at the angles and ask yourself questions like, where's this angle? Is it part of a shape? Is it part of a triangle? Is it part of a cyclic quad? Where is it? Is it at the circumference? Is it between a tangent? Things like that. And based on those questions, you can use certain theorems on them. So with angle S3, I'm looking at this and I see that we have lines going across, but I'm not going to start saying, oh, it's equal to this. We can figure it out first and then write it down so that we don't end up writing things that we don't need. Okay, so I do see that it is equal to S6 because of vertically opposite angles, but then I can't really see how S6 can move. Okay, do you see that they told you that this is a cyclic quad, right? So it can move, but I don't really think you needed to say it's equal to S6. So here's what I mean by this. If you start at angle S3, right? Do you see that you have a cyclic quad over here? And what do you know about the exterior angle of a cyclic quad? So that is angle S3. It's an exterior angle. The exterior angle of a cyclic quad is equal to the opposite interior angle. So we have these two being equal. Let's hold on to that. Let's see, can this move, to anywhere that can at least get us to get to S4? Because that's what we're trying to do, make S3 equal to S4. So we're here now. Can that move? Where can it go? So I'm going to think about the fact that I don't have a center, unfortunately. So I can't use theorems like the angle at the center is twice the angle at the circumference. There's no center, but it is at the circumference. So let's think about that. If it's at the circumference, we have to use theorems that have to deal with angles at the circumference. There is the bow tie theorem, okay, the one that crosses like that. But as you can see, that doesn't cross. It's just an entire angle here. But then there's also this theorem that people always forget refers to an angle at the circumference, and that is the tan chord theorem. See, the tan chord theorem has to do with, because that angle that they are speaking about, it has to be at the circumference, okay? So that the angle between the tangent and the chord is equal to that angle at the circumference. So with that, do you see that we have a tangent? This is a tangent, AR. If that is a tangent, this is our chord. The angle between the tangent and the chord is this, and that is going to be equal to the angle supported by that same chord, which is angle Q. Okay, so we can see that this entire angle ARP, is also equal to it. But let's just keep going. I don't want to just start writing it down just in case we meet like a dead end. So let's just see. When we get to this point, the only place I can see that this can actually move from, do you remember that this is a tangent drawn from the same point, okay, to the circle, tangent drawn from the same point to the circle. So these two lines are equal, meaning we have an isosceles triangle here. And so these angles, the angles opposite the equal sides would be equal. So we get to this point, and then after this point, it being equal here, I can't really move this further. Okay, unless I'm moving it again. See, do you see angle between the tangent and the chord is equal to the angle? So it just gets back to this. So I don't think this is a good idea, and this is how I'm going to take away my steps instead of, so you do this with a pencil, okay? So we're not just going to just rule out everything and say, okay, it's not going to work. We can't do that. What I'm going to do is go a few steps back. Let's remove that because that clearly didn't work. That took us to a dead end. So let's just see. From here, can we get to anywhere else other than this point over here? Okay, do you see that we have these two lines being equal? So we have another isosceles triangle. So this is an isosceles triangle, meaning the angles opposite the equal sides are equal. The base angles, right, are equal. So we have now R3. Okay, can we move R3 anywhere? Let's think about what R3 is. Where is it? It is, yeah, it's close to the tangent, but it's not very useful because of how it is right now. It's not the angle between a tangent and a chord, okay? It's kind of just between two chords. So we can look at it as an angle at the circumference. And you can see now that it actually forms this bow tie theorem. So the angle at the circumference, right? And this angle here, the angles at the circumference supported by the same chord would be equal. So we've got R3 to jump to S4. There, we've done it. Okay, so that actually got it to that point. You see, you are actually taking the angle and letting it travel. And then you may meet some dead ends, but then when you do, you erase and just go a few steps back. Okay, like we did with that. So we stopped here. So we decided to take a different approach, a different road, and we got to that. And so you see that it does get you to angle S4. So now we can go ahead and start writing this down. So we know where we started. We started from angle S3. And we found out that angle S3 was equal to this big angle Q, because this is a cyclic quadrilateral. And that was the exterior angle of the cyclic quadrilateral. So we can go ahead and put that down first. So we're saying that angle S3, that pen is too big, angle S3 is equal to, and it was equal to this angle. I feel like I can call it angle Q. I mean, it is the entire angle Q, but let's just be specific. Angle RQP. Okay, so that's what I'll just call it, RQP. And the reason it's equal is because of the exterior angle in a cyclic quad. Okay, so we have that done. And then remember, we went from Q to angle R3 because these two lines were equal. So you can, if you would like, tell them that the two lines were equal. I'll tell them first of all that we knew that PQ was equal to PR because you guys told us that. Okay, so we'll say given. So PQ equals PR because it is given. And because they are equal, we have an isosceles triangle. And so these two angles are equal. So that angle RQP is equal to angle R3. Okay, so let's go ahead and tell them that. And the reason here is not really isosceles triangle, but angles opposite equal sides are equal. Okay, so we got that down. And then we found out that because of the bow tie theorem, okay, angles in the same segment theorem, because these go across like that, the angles at the circumference supported by the same chord are equal. So angle R3 is equal to angle S4. So angle R3 equals angle S4 because of angles in the same segment are equal. Okay, so you see how we got angle S3 to be equal to angle RPQ, which is equal to angle R3, which was finally equal to angle S4. Okay, so ultimately angle S3 is now finally equal to angle S4. So we can conclude that. Therefore, angle S3 is equal to angle S4. And there we have proven that. Okay, that was for 5 marks. Moving on to the next question. So I'm just going to clean these up because, yeah, these lines are really complicated. So we're just going to really maybe just put those markings to be really small, but they need to be there because it's going to help you with the next question. Okay, the next question, 10.2, says we need to prove that SMRC is a cyclic quadrilateral. So SMRC is over here, SMRC. So I'm just going to draw that out properly. Okay, so this is what we have. To prove something is a cyclic quadrilateral, okay, I have explained this before, but there are 3 ways that you can prove that a shape is a cyclic quadrilateral. The first way is if you have a circle and you have a quad inside the circle, okay? It's not a cyclic quad yet, call it a quad for now. And then if you notice that the exterior angle of this quad is equal to the opposite interior angle, then this is a cyclic quadrilateral. The second way to prove that something is a cyclic quadrilateral is when you have a situation like this. So this is not necessarily a quad, but it is this situation where the lines go across like that. And then you find out that these angles here at the circumference supported by the same chord or arc are equal. Then that is a cyclic quadrilateral. And then the third way to prove that a shape is a cyclic quadrilateral is when you have a quad inside a circle and then you notice that the opposite angles, they add up to 180 degrees. Then you have a cyclic quadrilateral. So let's go ahead and see which one could work for this. Straight away, I don't even want to use the opposite angles add up to 180 degrees because I have not, throughout this whole thing that we've been going through, I have not seen any indication of a 90-degree angle even. So I'm not really going to focus on that one too much. If it does work, we will use it though. But the one that I feel would work the most here, just because of the way the shape looks, is the exterior angle of a cyclic quad. Okay, so I would have loved to use the angles in the same segment, but you see that lines do not go across like that. Okay, so we can use the exterior angle of a cyclic quad. So do you notice that this quad actually has multiple exterior angles? It has an exterior angle here. So we would be trying to prove that angle S1 is equal to this entire angle. Okay, it also has an exterior angle here. So we'll be trying to prove that angle C1 is equal to angle M1. It also has an exterior angle over here, meaning we will be trying to prove that angle M4 is equal to angle C2. And it also has one over here, which is proving that this entire angle R4 and 3 together are equal to this angle. But the one that mostly relates with what we already have down, okay, things of what we've already found are equal to each other, I would go with S1 because that one, you see that S1, because of these lines that go across here, will be equal to angle S4, so vertically opposite. So we already have it equal to something that we have. So this is actually working out well. We just have to ensure that angle S1 at the end of the day is equal to this angle over here. Let's just call it CRM. because it's in that cyclic chord. So angle CRM, that is what we will be required to prove. So we can write that down. We are required to prove, I'll just say RTP, it's just for you to write down. Nobody's really going to look at this when they're marking, okay? They don't really mark that. So we're saying that angle S1 should be equal to that angle CRM, okay? So angle CRM. Okay, let's see, how can we make that happen? How is that possible? Okay, I think this one works out really, really well. So the thing is, do you see that these are already vertically opposite? So you already have them being equal, meaning angle S1 and S4 are already equal. But then for this angle, do you see that this angle CRM that we referred to, it's actually the angle between the tangent AR and this chord RP, right? So it will be equal to this. It's one of the things that we already found when we were trying to find the first question, but we left it because it wasn't working for the first question. Okay, so the angle between the tangent and the chord is equal to the angle supported by the same chord. So those two are equal. But we also know that angle S4 is equal to angle S1. So those two are equal. But the thing is, we've already proven that S1 and this angle are ultimately equal. So that would make these two now equal. Okay, so we just have to write it down. Okay, for the sake of using this again, and I feel like we should have also done that for like these bigger angles, we can just call them what they are individually. So add it together. So instead of calling this CRM, we can call it angle R1 plus angle R2. Likewise with this one, RQP, instead of calling it RQP, we could have just called it Q1 plus Q2. That would just make it easier for us to remember what it was so that we can just better work through it in equations that we're going to form here. Okay, so R1 plus R2 is what I'm going to call it instead. Okay, and I just decided to change it here as well, just in case it's helpful. Angle S1 is equal to angle S4. Okay, so we're first making it equal to that because those are vertically opposite. So we have angle S1 is equal to angle S4, vertically opposite angles. Okay, and since those are equal, we have that done. But then we're also going to refer to this angle here. So that's that angle R1 plus angle R2 because it's the angle between the tangent and the chord. So it's equal to the angle supported by the chord. So angle R1 plus angle R2 is equal to angle Q1 plus angle Q2. And this is because of the tan chord theorem that we have over there. Okay, so we're done with that. But then we should also remind them that we already knew that angle S1, we found out previously that angle S1 was already equal to this angle, okay, that RQP, angle Q1 plus Q2. So let's go ahead and tell them that. But we know that angle S1 is equal to angle Q1 plus angle Q2. So because we already know that they're equal, as you can see, we have already proven that in the previous question, since angle S4, right, was equal to angle S3. Okay, angle S4 was vertically opposite angle S1, which we've already shown them. So since these two are already equal, then that makes these two equal. And so angle R1 plus angle R2 is equal to angle S1. And now you see that that actually proves the exterior angle of a cyclic chord theorem. That's actually showing that over there. So therefore, angle S1 is equal to angle R1 plus angle R2. And you can see that here. Do you see that they're both equal to angle Q1 plus Q2? Therefore, they are equal to each other. Okay, so there, we've proven that. If you like here, just to show that, yes, we know that these two are equal, is because they were already equal to angle S4. Okay, in the previous question, angle S4 was already equal to angle Q1 plus Q2 because it was equal to angle S3. Okay, so there, we have that done. Okay, so now that we've proven that those are equal, we can now conclude that this shape is a cyclic chord because you have an exterior angle being equal to the opposite interior angle in this chord. So remember, the name of the shape is SMRC. So therefore, SMRC is a cyclic chord. Okay, and we can see because the exterior angle of the chord was equal to the opposite interior angle. Or you can really say it's the converse of the exterior angle of a quad theorem. Okay, and it's a converse theorem because we were not using the theorem. We're actually showing them that that is a quad because of that theorem. Okay, so that is done. That is 10.2. And then we move on to 10.3, which is the last question for this paper. Okay, we're on the last question, question 10.3, and it says, RP is a tangent to the circle passing through, we have to prove that RP is a tangent to the circle passing through P, S, and A at P. So it's a tangent at P. Okay, I'm going to bring down the diagram because it's going to help us a lot. I don't think we need these lines anymore, really. Just all the angles that are equal, those are very important. So we need to leave those there because they're really going to help us throughout the questions, just so that we already know what is equal to what. Okay, I'm going to use this diagram. Okay, here's our diagram. So here's what they are saying. They want us to prove that there is this line RP. Okay, because we have so much reds, let me use something like blue. So this line RP is a tangent. We need to prove that this is a tangent passing through the circle. So passing through a circle that passes P, S, and A. That's what we need to prove. So P, S, and A are here. This doesn't look like a very nice circle, but it's fine. We'll just see what we can do here. Okay, so we're going to have a circle here, and then we need to prove that that is a tangent to that circle. Okay, so this is what the circle looks like. We have a circle, and we need to prove that RP is a tangent to this circle. So let me just note a few things here. First of all, in this circle, the circle has some chords. Because RP is a tangent to the circle, and the circle passes through A, S, and P, that would mean that SP is a chord. That also means that SA is another chord, and we also have AP being another chord. So when proving that something is a tangent, like in this situation, we don't have a choice. We can only use this theorem. The theorem where you have a circle and you have a tangent. If you can prove that the angle that lies between this, that is supposed to be a tangent, right, and that chord is equal to the angle supported by that same chord, okay, then this is going to be a tangent that you have over here. So that's the idea here. So if you see this, you're looking at this, the angle between the tangent and the chord that we need to look at would be angle P2. And I'm starting to realize that all of these, they just need to be in a brighter color. So I'm going to choose a brighter color to use here. Okay, I think that looks just more visible now. So now that we have this, what we're really trying to prove now is that the angle between this that is supposed to be the tangent and the chord SP, you see that that angle is this angle over here, P2. We need to prove that this angle is equal to the angle supported by this chord SP in this purple circle, okay? And that would be this angle A2. That is what we're required to prove. So I'm already going to say that we are required to prove that angle A2 is equal to angle P2. Okay, so let's go ahead and do that. We're using this theorem. Okay, how can we actually start with this? Well, it's a good thing that all of these are already underlined, highlighted and stuff. They're already marked. So we know all the other angles that are equal to each other already. Well, the way this is looking, as you can see, A2 is right at the edge. It's not a very nice angle to try to use to move around. Like, I can't really find anything that is equal to A2 just because of where it is. It's in a very awkward place. But I can move P2 around, okay? I see that I could say that angle P2, because of angles in the same segment, I could say that angle P2 is equal to angle Q1. As you can see, like this, okay, because of angles in the same segment. But then after that, then what? What can I actually do here if it's equal to Q1? What else is equal to Q1? Well, Q1 is at the circumference, so we can use theorems about angles at the circumference. We can use that tan chord theorem. So because Q1 is at the circumference, do you see that the chord supporting Q1 is this chord RS, right? So it would mean that the angle between this tangent and the chord RS, angle R1, would be equal to angle Q1. Is that helpful? Doesn't really seem helpful because I just moved from P2 to Q2 to R1, but how do I get to A2? That's the main goal. Okay, so looking at this, by the time we get to R1, we're stuck. This is a dead end. We can't really relate this to angle A2. I actually just wish that these two were parallel, because then we would just be like, oh, they're alternate angles. But no, they're not, so we cannot do that. Okay, so I'll erase. I'm not going to continue with that because that's not really helping, okay? Moving from Q1, I can't really move it anywhere else. I'm not seeing any place that I can move it other than there. And then when we get here, it's really just a dead end. So let's go back to looking at P2. So can P2 move anywhere else? Well, not on its own. And at this point, I think we're now supposed to try to just find equations that can include A2 and P2. Just because A2 is already not a very good angle to try to move around, just because of where it is. And if you even do try to move it around, it doesn't really move much. And P2, when we move it, we just reach a dead end. So here is option 2. Plan B is we're going to have to start seeing which equations can we form that are going to include the angles A2 and P2. So thinking about that, we can think about things like triangles. Okay, so triangles, but I'm trying my best not to include any physical angles like 90 degrees or 180 degrees, things like that. Okay, I'm just trying to create equations using what we have here, like triangles and the shapes that we have. Okay, so let's think about P2. How can we create an equation with P2? But it's best to make it relate with something that we already have. So look at what we have here. You see P2, there are a bunch of triangles that we can actually use here. So with P2, we can have this little triangle, but I just don't think that's a good idea because of M2. We haven't really found anything else that, relates with M2. Of course, you have M4, but then you see M4 could be equal to C2 because you have a cyclic chord here, exterior angle of a cyclic chord. But then it's a dead end again because of that C2 doesn't really have much to do with everything that is going on here. Okay, so I'll leave P2 for now. Let's actually try to form an equation using A2. Okay, so let's try to form that triangle that includes A2. So A2 we have here. Well, we can stop here, I guess, because you saw that that was a bad idea. So with this, the rule that we can use, using interior angles of a triangle is not a good idea right now because it's going to include the angle 180 degrees. Let's try to form equations without using physical numbers so that we can just relate these angles better. Okay, we have A2 and we have P1. And do you see that we can actually use the exterior angle of a triangle here? The exterior angle S4, that angle over there, should be equal to angle A2 plus angle P1 added together. And I'll write this down just in case it's going to, because I don't want to now have to remember these equations. So we are saying angle A2 plus angle P1, right? That when you add them, they should give you angle S4 because that is the exterior angle of that triangle. So angle S4. Okay, so we have that. And it's good that it's equal to angle S4 because angle S4 is an angle that, is equal to other things like angle S1, and it's equal to this angle over here, angle R1 plus R2. It's equal to angle Q1 plus Q2. It's already equal to things that we have. So it's not a bad idea to use that. And now let's try to also, because it's not enough really to just make these two equal. Let's try to form another equation that includes angle P2. So let's see how we can do that. Angle P2 is over here. And we could try using triangles, but the triangle that I see that would include angle P2 would either be this little triangle, which is a bad idea because of the M, or this triangle, which I do not like at all because now it's including S5 and S4. Okay, so what else do we have with angle P2? Okay, I see something with P2, but it's not just P2 alone. It's P2 and P1. Do you see that this is a tangent? This is a chord. Okay, so angle P1 plus P2, the angle between the tangent and the chord, will be equal to the angle supported by that same chord, angle Q1 plus Q2. Okay, that is very helpful because do you remember that Q1 plus Q2 is already equal to angle S4? So we can actually work with that. Let's try doing that. So angle P1, I'm going to say angle P1 plus angle P2. Those two angles combined, they are going to be equal to angle Q1 plus angle Q2. Okay, and that is because of the tan chord theorem. Okay, and now let's go ahead and play around with those equations and see how we can actually if we can make those two equal, because these two equations do include both of these angles. Okay, let's see. So we've got A2 here and we've got P2 here, and that's what we want to be equal to each other. But remember that S4 and angle Q1 plus Q2, they're already equal, like we've marked here. See, S4 is in red and Q1 and Q2 already in red. So these are the exact same thing. They're equal to the same thing. So I can actually tell them that. But we know that angle S4 is already equal to Q1 plus Q2 because we already proved this. And so because they're equal to the same thing, then it's like you saying something plus another thing is equal to the same thing. Oh, P1 and P1 are the same thing as well. So really, in a nutshell, if these two are exactly the same and these two are exactly the same, that concludes that angle A2 is indeed equal to angle P2. Okay, so that's how we actually prove that. And that was for how many marks? 6 marks. Now we have to just conclude. So we have proven now that the angle between the line that they said we need to prove is a tangent and the chord is equal to the angle supported by that same chord. So to conclude, you can just look at what they said, right? They said prove that RP is a tangent to the circle. So you can now conclude RP is a tangent to the circle passing through that point, and then we'll give our reason. And the reason for this, it's not the tan chord theorem because we didn't use the tan chord theorem. It is a tangent because it supports the tan chord theorem. So it's really the converse of the tan chord theorem. So our reason will be converse of tan chord theorem. So that is that one. Okay, they keep coming up with ones where you really have to think about it towards the end. So that is it for this paper, grade 12s and senior certificate students. And I will see you guys in the future videos in November 2024's paper. I wish you guys all the best, and I'll see you guys in the future videos.